Hello? Does it work? All right, so let me start. Let me welcome everyone. It's very exciting to have you all here for IGST 2025. Thank you for taking time to come into London. And if everyone goes as planned, we'll have 5 days of exciting talks and social events, hopefully allowing you to catch up with your friends and colleagues. In case you encounter a problem, though, let me give you names of my organizers and to give you some impression how they look like. So, but because probably it's not the most indicative image of the organizers, maybe it would be identify yourself if you like show. No, I mean maybe show your face, but okay. Anyway, so you can complete the picture. No, not yet. Not. No, keep it to the last day, you know, all this energy. Right, so there's some practical information. So please wear your badges at all times. Otherwise, securities are instructed to, well, let's not go into detail. Right, so please, if you registered for the conference dinner or reception, you should have tickets inside. If it's not the case, then something went wrong and we'll have to penalize some organizers. Well, probably my fault, to be honest. Right, so most importantly, obviously, everyone is welcome to connect to our Wi-Fi network, and as EDROM never works, you can still use the cloud. I think everyone should be able to register for that for free. But I should warn, during the talks, we'll of course switch off all Wi-Fi, and also mobile signal will be. Right, so for lunch, if you just proceed along this exit, you should find yourself just in front of the canteen, or if you want some more, I know, expensive, let's say, options, you can go outside. Obviously, we're in the center of London, so there are many options, but some of them are listed on our webpage, if you manage to connect to the Wi-Fi. So, because Volodya asked yesterday, so the afternoon coffee break is slightly bigger than the morning one. So, just special information. So, for posters, please identify yourself to organizers, and we have to put your posters for Tuesday poster session in between reception and end of the talks. Conference dinner will take place on Thursday. And it requires some walking from here, so maybe we'll start walking all together. Maybe I should register with police, quite a few people. Right, so because it's a bit raining this week, we also booked some rooms, and you can find them on the useful information page on the web page. But when it's not raining, you can use all the spaces outside. There are nice seats just to the left from this room when you go up on floor 0, or also on Strand, there are many nice places to sit. Right, so again, so if you want to find the room for discussion, you either need a really good sense of orientation, or you can ask Jeremy for details. But this is roughly the map of where to go. Yeah, it's all information is on the website, so it's just a small part of the practical information. Way more details you can find online. All right, and now I have to take a moment to acknowledge the unfortunate passing of Rodney Baxter, who died yesterday. So he was an obvious towering figure in our field, whose ideas laid the groundwork for the modern integrability and such things as the Young-Baxter equation, star triangle relations, the Baxter-TQ equation, and Q operator, something we'll hear this week many times. And just to mention a few things he discovered. and obviously he's developed many ideas which are cornerstone of our subject. And his influence is felt in near every talk on this conference, and I'm sure his legacy will continue to inspire generations of researchers to come. And I'm sure speakers will be mentioning him during this conference and maybe sharing some stories. All right, but so that we are not finishing on a sad note, let me also say that today we are celebrating 20 years of the IGST series conferences. So it's founded 20 plus epsilon years ago by the founding fathers. And let me announce that the next IGST slot is still vacant. So please submit your bids to the founding fathers before Friday, or to the founding kids like myself or Didina and others. So that's the end of address. Hopefully it didn't take too much of your time. And now I pass to Joe for chairing the rest of the session.
Okay, so as Golia said, this is the 20th anniversary, but it's also the 10th anniversary of IGST in London. So it's great to be back in London again. Okay, so I'm happy to introduce the first speaker this morning. This will be Ellie Pomoni, and her title will be News from 4D N equals 2 SCFT Spin Chains.
Thank you, Joe. It's a great pleasure to be here for the 20th anniversary and the 10th. My first IGST talk was 10 years ago. So let me thank the organizers for inviting me, and it looks a very exciting week coming. And this is a little bit of a topic that I think this is, if I have a legacy, at least for the IGST crowd, this is going to be what I am working on sort of my whole life, of course with other things. And yes. And of course this work, there is no way I would be able to do alone. There are some amazing collaborators, especially Denise has a poster. So this will be another spot to discuss about these topics that I will talk about today. My main concern will be to present this paper from last week. And there is another paper, parts of each of which you have heard before in previous IGSTs, but I want to try to show you like the way we understand things now. And without wasting any time, let's go to, okay, IGST. What is the biggest thing that came out of it? N equal to 4 super young means is integrable, and we are still working on being able to use integrability to calculate more and more observables. But if you stick to 4 dimensions, there is a big open question. I mean, when we write our grant proposals, we say that we want to go to QCD, so we really need to try, yeah? So what do you have to do if you want to try? So the first simplest step after n equal to 4 is to study n equal to 2 super CFTs. And the best way to do it, in my view, is to begin by orbifolding n equal to 4 super young mills, because what you get is integrable theories, and then perform marginal deformation. And by doing that, in fact, what is happening is that you are capturing a very big subset of the landscape of n equal to 2 theories. And this construction is also fantastic because it generalizes to n equal to 1 theories. So with this in mind, this is my favorite toy model, which you have all seen many, many times. So we begin by doing a Z2 orbifold in n equal to 4 super young mills. And then we marginally deform along the conformal manifold, which in this case, it's 2-dimensional. When the coupling constants are equal, we call it the orbifold point, which is the theory that we know is integrable. And as we go away, all the way to the point where one of the 2 couplings are 0, we obtain super QCD, n equal to 2 super QCD, which you could say is the most physical n equal to 2 super conformal theory. And the most important thing I want you to know for this theory is that happily in n equal to 4, all the fields were in the adjoint representation of the color group. Now we have two color groups, two SUNs, and I try to put color so that I attract your eyes. So there is one type of objects that are adjoined under the one, another adjoined under the other, and we have bifundamental fields. And I want to say that all the new physics really comes from precisely that. So let's go for it. So for this talk, I will first have a shut up and calculate approach. And this is really just explore how much can we do with coordinate Bethe ansatz. Up to very recently, we didn't even know how to write 3 and 4 Magnon eigenvectors. Now I will be able to write them down. And for that, we will see that long-range interactions appear. And then I will have a more beauty way, top-down, where I will search for new symmetries, and I will try to convince you that we need to go away from the Lie groups that we love. We need to go to groupoids or category theory if you like more math. This is the future. So let's begin with a shut up and calculate approach. So, and I really tried my colors, so let's start. First of all, n equal to 4, let's say it has the two x and z fields, and they are rotated by a subset of the SU, of their symmetry, which is an SU2 rotation. But the moment you do the orbifold, this is broken. So naively, we do not have it. Now, when you try to construct vacua, if you do a ZZZ type of thing in n equal to 4, now you get two of them. And I try to label them with the two colors, blue and pink. So this is a very important thing for this talk. And there is another type of vacua, which is bifundamental vacua. And these we're studying in this paper, and I will not repeat anything other than showing you this equation and make you want to ask questions at the end of the talk or by the poster. So this talk will be all about this. So here we are. One Magnon around the ZZZ vacuum. So this bifundamental excitation, precisely because it's bifundamental, it interpolates between the two different vacua. And there is no other way. There is no way out of that. And because we have the Z2 of the orbifold, there are, in fact, two one Magnon eigenstates, and they are Z2 conjugate to each other. And this is their energy, one Magnon, and you see this is very different from this. Yes? So there is some very rich physics in this model. And also, if you do Z2 together with parity, is precisely equivalent to reading the chain backwards. Now, two Magnons were also, this is my childhood, that's why I said now I feel old a little bit giving this talk. So there are again there are two eigenvectors. And in this time, we interpolate between one type of vacuum, we change to the other, and then we go back to the other one. And they are again Z2 conjugate to each other. And when we look at the amplitudes, the scattering coefficients, they come with a pattern. And the pattern is precisely, so this is you can say the XXZ scattering matrix with anisotropy parameter kappa. But now, both of them appear, one with kappa and one with 1 over kappa, where kappa appeared here is the ratio between the two coupling constants. Yes, it's the way you go from red to blue. And yes, you should really think that these things are colored. Now, what is going on and why it has taken so long to make progress? If all you know in life is coordinate Bethe ansatz, and you try to find a solution for 3 or more Magnons, you will simply fail. And you will not only fail if you just try coordinate Bethe ansatz, even if you add contact terms, a finite of them, you will still fail. There is no way to do that. So what we had to do, and the reason why you fail is precisely because the naive Young-Baxter equation is not satisfied. And this is why the colors are super nice, because now you can follow this guy is this guy, this guy is this guy, and so on. And you see how you should put your S matrices, and they fail. So what did we have to do in order to succeed in finding eigenvectors? By the way, this is a physics problem. It has nothing to do even with integrability. You should be able to find eigenvectors, yes? So what we had to do is we had to allow, at least for the infinite chain, for an infinite number of position-dependent corrections to the coordinate-based ansatz. It's almost like saying we don't know anything, we admit we are stupid, we will try the most general thing we could ever do. So this is the original ansatz now for 3 and for 4 magnons. We add these guys. And n and m and also r here are integers, which precisely label the distance between the magnons. So the way now you understand is you set up your problem and you try to solve the eigensystem. And what you find is that these d's, the corrections to the coordinate-based ansatz, they arrange themselves in a lattice, which is here. I first will explain the 3 magnum, and then you can imagine in your head the 4 magnum. So these are the distances between the left, and these are the distances between the right. And the eigenvalue equations, they arrange in 3 classes of equations, where the 3 magnons are far away all from each other, when 2 magnons are near and 1 is far away, and when all the magnons are all next to each other. And the colors that I have here, they tell you what they are solving for. Yeah? And again, for 4 magnons, you should imagine the same thing, but in a form of a cube. And what is important is that for any d, these equations, if let's say you want to solve this guy, they relate them with their nearest neighbor. So you are solving like a little cross. And of course, all the crosses are related to each other. So you do this, and you start solving, and you discover that if you only impose these eigenvalue equations, you can in fact not fix all the coefficients. And this is okay, we are not crazy. This makes sense because we have not yet imposed any boundary condition in this infinite chain. What we will do, because at this stage we don't want to impose boundary conditions actually, is we will do a trick. We will remember that there is this very important Z2 symmetry of the quiver, and we will try to have further conditions on the ansatz such that this Z2 symmetry is always manifest, first of all at the level of the infinite chain, but also, and this is a little bit a posteriori, I have to say, when you take it and you close it and you impose periodic boundary conditions, twisted or untwisted, we want whatever we get to match with what we get with direct diagonalization, yes? And we discovered that this is a good thing to impose. And I challenge you to find something better. Now, here we are. We have this guess, if you wish, something that divine intervention. And then we plug it in our equations. First, the 3 magnum, and we start fixing, we start getting answers. So we get these 3 guys. Then we plug it in the 2 magnum interacting equations, and we start getting the blue guys. And we continue to this area, and we get the green guys. And what is happening, you see what is happening. You always have these factorized scattering coefficients. You always have this kappa minus 1 over kappa, which is fantastic because when kappa is equal to 1, the 2 couplings are equal. This goes to 0, there are no corrections, and you go back to what you know and love for normal coordinate-based ansatz. And then as you start going to bigger and bigger distances, you get this parenthesis in front of this factorized beautiful part, which they have the energy of the 3 magnons, the total energy and the total momentum, and sometimes also other momenta start coming in this parenthesis. I will not bore you with writing huge, horrible expressions. So the point of this exercise is for this special solution that we started with this assumption, if you wish, you can completely solve for all these coefficients, and they have this very beautiful factorized form, and they can also be captured in a generating functional. And I want to say that the power of which we are not even close to comprehend. But you can ask me. Fantastic. So we have the solution now, and we want to ask for its properties. And first of all, already the scattering coefficients, they factorized, so they just obey the Young-Baxter equation. Now, what is remarkable is not this. What is remarkable is that also all these crazy corrections, infinite numbers of them, in fact, they also obey some type of Young-Baxter-like equations for all the integers. And here I write for you what they obey for the 3 magnum problem. This Y is an object that you could define as the Young operator. It's the thing that appeared in the very first paper that Young wrote. And I write it here. I don't really want you to look closely because you will maybe, it's too much. And it's also unitary. But we have this infinite tower of equations. This is not magic. There is a reason, right? Now, not only that, there is something even more amazing, which is in the paper that came out last week, which is the following. Now we have a way to relate an n+1 Magnon eigenvector to an m Magnon eigenvector. How do we do that? We do something that I like to call smearing a Magnon. So basically, you allow to sum all the possible, you pick your favorite Magnon, let's say the one on the right, and you sum over all the positions it can take. And also you have to localize it by setting its momentum to 0. The moment you do that is a simple exercise to see that the 4 Magnon eigenvector gives you the 3 Magnon eigenvector. And this is, by the way, this we also started testing with XXX, XXZ. This only gives you factorization. But of course, here it gives you way more things. It gives you relation between the 4 Magnon Ds and the 3 Magnon Ds. And the best way to see the consequences of this crazy equation is to think at the level of the generating function, which captures all the Ds. So first of all, by taking limits, you can see that, for example, if you are smearing all the right one, the right Magnon, this is equivalent to taking Z to 1, and you relate directly the 4 with the 3 Magnon generating function up to a very concrete pole. If you do this for the middle guy, you get a finite answer. And clearly also, if you do this for the x, you get the same, but the pole has here 1 minus P1 x. So then this becomes like OPE game in 2D CFT, and we love these games. And you can do it, and you can patch the poles together, and you get an answer. Clearly here, I'm not presenting all the details of the answer, and it's a 3-line thing in the paper with also references to the appendix. But you see what happens. This 4 Magnon function, it organizes according to the poles. These are 3 Magnon stuff, 3 Magnon stuff, 3 Magnon stuff. It's an amazing equation. Now, why this is happening? This is really crazy. The reason why this is happening, as I will try to convey, is that there are more symmetries than we thought are there. Of course, we are only at the beginning of really understanding what they mean, but let me try to tell you what they are. So the most important thing, if you want to think about in terms of symmetries, the most important thing I want that it stays with you is that n equal to 4 super Young Mills was a very lucky thing. All the fields are in the adjoint representation. So the only thing you could put on a lattice side was an element of the singleton representation of n equal to 4. And the total space of spin chains, is this beautiful product. And I have to insist that all the chains that we know how to solve, they are only of this form. We don't know how to do other things professionally. So what I am trying to tell you now is that if you want to go beyond n equal to 4, and here I'm talking about n equal to 2, but n equal to 1 is the same, you are not having unique singleton representations anymore. You have at least 2 distinct ultra-short representations of the superconformal algebra. So this beauty is out of the window. That's the most important thing to remember. This is out of the window. And let me elaborate on this. So precisely because we want to be in the planar limit and we want to color contract matrices, the one after the other, some orderings are allowed. For example, here, 1, 2 can go after, but some other things are not allowed. If you end with the 2, you cannot start with the 1. This will give a off-planar contraction. So in this paper already, we had found at least a physicist way to talk about this by saying that these spin chains are dynamical. And what we meant by that is that you can always think of n equal to 4 states as the mother theory, and then go and choose your very first index. Here is 1, here is 2, and then just color contractions will give you the rest, and there is nothing for you to decide. Now, in this paper, we have I think, the most elegant way to describe this phenomenon, and that's actually the only way also to talk with mathematicians. And this is that the Hilbert space of these spin chains, it forms a path groupoid. And what is a path groupoid? It's something super simple. Here is the picture of the quiver. Follow the arrows. As long as you are following the arrows, the operators you are making are correct. And this language is basically precisely the language that is used by Felden and Wren in this beautiful paper. And it is a one category. I'm not going to tell you any crazy math here. I just want you to remember, follow the arrows. That's what it is. Now, that's not all. There is even more symmetry in the game. And that now the R-symmetric algebroid, we call it, if you don't like, I'm not attached to any name. This is what acts on these spin chains. So in n equal to 4 super Young Mills, very happily, we had an SU2, and the X and the Z, they were forming a doublet of this SU2. Fantastic. Now, as I already said, we lost this SU2, and the reason is clear. You cannot put in a doublet oranges and apples together. It's not allowed. And here is an orange, and here is an apple. This is adjoint, and this is bifundamental. The only way to circumvent this problem is to drop the Lie algebraic setting and go to a Lie algebroid. Let's do this. And let's do it as stupidly as possible so that no one cannot follow, basically. So in n equal to 4, we have a SU2 algebra, and we have raising and lowering operators, and they tell us how to go from X to Z. Now we have lost the SU2, but let me nonetheless define raising and lowering operators. Now I give them an extra index, an index 1 and 2, which has to do with the Z2, or the fact that I have two color groups, and I simply prescribe how they act. Clearly, these babies, they know about the color because this was an adjoint object and this was a bifundamental object. So this person is responsible for changing the color representation of this guy to this. Yes, so this is not just Lie algebra. Now, how should you understand this algebroid? Basically, you should just understand this picture, but let's walk through it together. This picture is only for single letter words. In a second, I will tell you how to string single letters to bigger words. And this picture, so these are the vector spaces on which we act. And these are the generators that tells us from where they start and from where they end. And in this picture, I have an extra element defined, which you can understand precisely from here what it is the mirror, is the Z2 symmetry of our quiver. It changes 1 to 2. And more explicitly at the level of fields, it makes Z11 to Z22 and so on. Yes? Fantastic. But you know, if I was just staying there, that would be silly. Things really become non-trivial the moment you start having at least two sites. So for n equal to 4 super Young Mills, we were very lucky, and we could use the trivial coproduct like this to act on two sites. And here I'm acting with the raising operator. Now, we have lost now this thing, but let's, for the beginning, be stupid and try the naive coproduct. The moment we do this, we get wrong, not allowed, because after 1, you cannot have a 2. How do we fix this? Our algebroid has an extra element in it, which is this gamma, this Z2 odd operator. So we change our coproduct to a non-trivial one by having here an explicit gamma. By the way, this is a little bit conventional. You could choose to put it here, but this is a convention that for us the first index is always important. Yes? And the moment we do this, the contraction is allowed, and this is a very good guy. And not only that, I can generalize this construction for any length simply by putting gamma, 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 gamma as many times as you need. And of course, the sigmas here are always the sigmas with the indices 1 or 2, that they simply obey a simple SU2 algebra. Now, fantastic. So we have some construction going on. Now let's take this and let's try to see what this does to the Lagrangian. First of all, before even doing that, we have to remember that the Lagrangian is a single trace operator. So to do my calculation nicely and also being able to show it to you, I will cut open the trace. And to do that, I need a prescription, and this is my prescription. I'm not the first human being to think about that. And with this prescription, I will show you an explicit calculation that this SU2XZ is a symmetry of the Lagrangian. This is the guy that was supposed to be broken and lost. And in fact, the whole SU4 is there, but I will not show this to you because I only have 30 minutes. And the fastest way to do the calculation is to use superfields, although in the paper we also have done everything in component. We went through all the pain, and there are many pages really doing this. So let's just do the superpotential. Here is the superpotential at the orbifold point where the two couplings are equal. We cut it open. This is the cut it open superpotential. And we simply apply the coproduct the way I showed you. Things just beautifully cancel. I put my colors to show you how things cancel, and you get 0. This is the symmetry of the superpotential. And Kähler also trivial is, the Kähler part is also trivial because it's a singlet. That's not enough. We want to go away from this orbifold point and capture the whole conformal manifold. How do we do this? The way we should think is that this coproduct that we wrote down, it somehow has to get deformed by the marginal deformation, which is this ratio of couplings. So this, as you will see in a second, it's captured by a Drinfeld-like twist object, which you simply read off from the F terms. And if you want to do the full SU4, you also have to include the D terms. This is something we understood when we were at MBI. And if you also want a physics understanding of this, it all comes from Seiberg and Witten. When there is a B field transverse to our D3 branes, open strings ending on these D3 branes see a non-commutative geometry. This is what is happening. Here is the twist. It does precisely that. It puts G1 and G2 here in the equation, and also deforms the coproduct the usual way. So we compute in this way, and we get this answer. So all that happened with respect to the previous equation is that I dressed my guys. By the way, again, this is only for the SU2XZ. If you want to go to the full SU4, pain starts. So you simply dress by kappa to a power, and this power is an operator that asks the field what is your first open color index, and you get 1 if it's 1, and you get -1 if it's 2. And this object also commutes with gamma in this way. So we have a construction, and we do the same thing. The only difference now is that there is G1 and G2 in the superpotential act. Everything is in the way that it's made to work. Super quickly, we didn't only stay into this. We also tried to use this symmetry to construct multiplets spectrum. And these multiplets are, I mean, it is very surprising that they exist. So for example, when we study n equal to 2 theories, we have Coulomb's and Higgs branch operators, and actually also mixed branch operators. And for n equal to 2 superconformal algebra, they have nothing to do with each other. Well, now with this coproduct, you can start from a Higgs branch operator, act, and make an SU2 multiplet relating all of these guys. And not it's just that you are having fun. These things, they come with kappas. So G1, G2 is everywhere sprinkled. And if you brute force diagonalize your Hamiltonian, you can check that you get these kappas in precisely the right place. So this is pretty amazing. And we also were able to do for 2 sites, for the full SU4, here is the 20 prime, and here is the 15. There is no detail here, but clearly the kappas are where they need to be. Fantastic. So let me summarize what we have. First of all, I gave you a generalization to the coordinate Bethe ansatz that has long-range interactions, infinite of them for the infinite chains. And doing this, I was able to obtain 3 and 4 Magnon eigenvectors, which were not there before. These eigenvectors, the coefficients in front, they go all together to conspire to form an infinite tower of Young-Baxter-like equations for every integer that signifies the distance between the 2 magnons. Not only that, the 4 Magnon eigenvector that we calculated explicitly and the 3 Magnon eigenvector that we calculated explicitly are related to each other in like a very interesting way. Yeah. This is something that I only said in one sentence, but it's important. By imposing periodic boundary conditions to the 4 Magnon solution, we can check that we get the same thing as direct diagonalization, so no bullshit. And there is a novel groupoid structure. In fact, there are 2 one-category structures which form a bicategory together, if you like math words. And we check the Lagrangian and a little bit of spectrum. And there is a plethora of things to do. This is a completely, this is just a few things that came into my mind that I should say, but please ask me and I will tell you more.
So we have time for a few questions. Nicholas?
Thanks for the talk. Do you consider your model integrable in the first place? I mean, I think there is a fundamental difference between an integrable model and a non-integrable model. And even if the model is non-integrable, there might be methods to address it, right? Even, I mean, especially if it's nearby to an integrable model. But is it integrable?
So at this moment of life, I will remain agnostic because I want to be super careful. Although I want to say something, which is, I think, very important. I think this type of stuff, a normal integrable person would not be able to understand. And that's why I really stressed the category structure. Like a normal person that is raised with XXX and XXZ and even XYZ cannot understand this paper. And there are matrices and Young-Baxter equations and everything. So basically what I'm saying, there is definitely more structure. I cannot at this stage tell you if it's integrable or not, but the only way to answer this question, you have to go to this game. There is no way out. Otherwise, you are simply asking the wrong question.
And then maybe just a very short one. Do you close your traces with different colors? Can you do that in a gauge?
No, so if the outside has different colors, you are not allowed to close them unless you put a defect. I am only closing when the same color is outside. That's why I closed only 4 magnons and not 3 magnons.
Adina? Oh, she's up there.
Yeah, thank you for the nice talk. I wanted to know if this structure of the smeared magnon is also present at the orbifold point.
It is trivial for the orbifold point because these G's that I had, they are actually equal to 0. So there is nothing to learn. Yeah, it's here. This is directly equal to 0. So you have to go away to see this thing.
Okay, thank you.
Are there any more? If not, since you have the slide up, can you say a little bit more about what the H's and the C's are?
So the H is the Z2 conjugate of G.
Okay.
So, you know, you solve and there is blue and red and there is red and blue.
Okay.
And this is something that has G's and H's in it. It just looks ugly and I packed it all in an H.
That's the one that's 3 lines or something?
Yes, that's pretty ugly.
Okay. If there are no more questions, let's thank Ellie again for a nice talk. And so I guess we have our coffee break now, and we'll reconvene at 11:25.
2, 1, 2, test, 1, 2, check, check, 1, 2.
So the first level, I can hear you.
One, two, test, 1, 2, check, check, 1, 2, 1, 2.
The other thing is that in case someone does want to answer a question with whiteboard or visualizer, someone has to toggle. So it's actually kind of annoying that people are sitting there, because it's best one of us should be there. Or Nikolay doesn't. Probably it's best that one of us doesn't. Or I just stay the whole time.
About Fredholm determinant in supersymmetric gauge theories.
Okay, thank you. Can you hear? Okay. My name is Bersa Boldis from Hungary, Wigner Research Center for Physics and Budapest University of Technology. First of all, thank you for the organizers to giving me an opportunity to present here in this nice auditorium in the center of London. So, as it was introduced, my talk will be about determinant in supersymmetric gauge theories. This is a joint work with my supervisor Zoltán Bajnok from Wigner and Gregory Korczemski from Paris-Saclay. So, what I'm going to talk about in the next 30 minutes is first I introduce a bit the ADS-CFT correspondence, or more like its parameter space, to be more able to understand what our results are. I'm pretty sure that most of you are familiar with ADS-CFT correspondence. But anyway, and after that, I will talk about these so-called determinant observables. First in general, and after that I separate them to two different classes based on 3 papers from the last year. So let's go. So first, as I mentioned, ADS-CFT correspondence. So ADS-CFT correspondence connects quantum field theory on a flat background with one on a geometrical background. Especially in case of the usual ADS-CFT correspondence, you have the ADS5 space on one side, and what you find is geometrically it has a conformally flat boundary, and then you can take some conformal field theory, especially N equals 4 super Yang-Mills theory on the boundary, and what you find are the observables in this conformal field theory are can be related to string theory observables on the ADS background. So it's okay, but we have like several parameters in the two theory. For example, string tension, Yang-Mills coupling, also the rank of the gauge group, since N equals 4 have this nice SUN gauge symmetry. After that, matching everything together, mixing them, you will have effectively 2 important parameters. One is the rank of the gauge group, or 1 over the rank of the gauge group. This is, I denote this by NC here, and the Toft coupling. So in the next, in my presentation, I will talk about the planar limit, mostly the planar limit, which is the n goes to infinity limit, so leading order or next to leading order in it. So we killed one parameter. The other one is the Toft coupling, which we are interested in. So in this case, we have like 2 different choices what we can consider. Either we can consider the weak Toft coupling limit or the strong Toft coupling limit. So from the weak side, you can basically do perturbation theory in the conformal field or the gauge theory. This is the red curve here. Or from the strong side, you can do with some magic perturbative string theory. But what's the main point of the ADS-CFT correspondence? In the middle, if you are precise enough or get enough coefficients, you will have some matching in the middle. But of course, since these are just perturbation theories, you will never have an exact matching, but you can try. And of course, there are some other problems as well. So in most of the cases, if you do perturbative gauge theory, you will have a finite radius of convergence after adding everything up, so it breaks down at some certain value of the Toft coupling. And also there are some problems from the string theory side, because you find that if you take the perturbative series, you will have factorially growing coefficients, which means that the series cannot give you any meaningful physical quantity, and you can also contain exponentially small perturbative corrections. So what I will talk about is exactly this strong Toft coupling limit, and I will explain in certain cases for this determinant observable how you can compute effectively to any order the 1 over lambda corrections and the exponentially small corrections. So what are these determinant observables? I will explain what this determinant means, but first I will just list some of the examples what we considered. So for example, as I mentioned, in most of the cases we are investigating the n equals 4 super Yang-Mills theory. There you can construct some physical quantities, for example, the cusp anomalous dimension, which comes from the expectation value of a Wilson loop with a cusp, or the octagon form factor, which is some 4-point correlation function of special operators. But you have also like scattering amplitudes. Also, there are some different models, for example, n equals 2 super Yang-Mills theory, where you find similar quantities. Also, there is random matrix theory, where you find a similar quantity, the Tracy-Widom distribution, which gives you some eigenvalue distribution of random matrices. But each of these quantities have something in common. And this is that for arbitrary Toft coupling, which I will, from now on, I will denote them by G because it's more suitable. In each of these cases, your observable is given by a determinant of semi-infinite matrix. So first, I will talk about those quantities that we considered in these two papers. For example, the octagon form factor in n equals 4, or the free energy on the sphere in n equals 2. And so since this is only the second talk and we already had a coffee break, I will get a bit more into technical details, but I hope it won't be too much. So what we are interested is that the strong coupling expansion of these determinants. So each of these cases have the same structure. The matrix elements of this semi-infinite matrix K and M is given by an integral of some Bessel functions and some symbol. I mean, it's just a function. I will refer to them as the symbol of this problem. This function chi can be chosen arbitrarily. So in each cases, you have the structure integral of Bessel functions put into an infinite matrix and calculated its determinant. It sounds like a very hard problem, but with some modifications or tricks, you can make it easier to deal with. So as you can see, you have also another parameter, this curly L, and by fine-tuning this chi symbol and this parameter L, you will have different observables in different theories. So let's talk about this symbol. So this is actually the essential part, how you can get the non-perturbative coefficients to understand its analytical structure and so on. So if you do some Wiener decomposition of this symbol, I will denote this with phi. So this phi has only poles and zeros on the positive half plane. So you can do this, also introduce the small x behavior of this function and so on. You can break down the whole problem into these kind of parameters even more, not functions now, only just parameters and numbers and so on. So here you can see the previous three examples. For example, you have this L parameter, and also you have the location of zeros denoted by xn and the location of poles. Actually, what will be important for us is the location of the zeros of this symbol function. So previously, it was shown by Belitsky and Korczemski that how actually the strong coupling expansion of these determinants behave. So there are some terms, divergent terms proportional to G or log G. There are some constants. It was previously defined. And there is the perturbative part, which goes in powers of 1 over g. So they already calculated and built up some very nice machinery to calculate these perturbative coefficients a, k plus 1. They contain, as you see, the parameters that we define and some integrals over the symbol. You can just leave it like that as also as some parameters or something, or calculate it numerically. Anyway, the main point is that they gave a machinery. I will talk about in more details how you can determine these coefficients, getting the whole perturbative part of the observables. But if you put in, so like choose one specific example from these observables and put in these parameters, you will find that actually these coefficients grow factorially, so they cannot have any physical or mathematical meaningful resummation. So you need to include exponentially small corrections as well. And this is denoted by delta f here, and they goes, actually, we will see how this actually goes, but they contain these exponentially small corrections, contain exactly the location of the zeros of this symbol function. And it is an infinite series of exponentially small corrections, and at every exponential level, you have infinitely many 1 over g corrections as well. So it's quite a huge problem to effectively get these coefficients up to any order in also in exponentially and also in 1 over g. So what their method was based on to get the perturbative coefficients. First, they rewrote the infinite matrix to an integral operator. Why is it good? So like this is an integral of also of the Bessel function acting on the function. This is how this integral operator acts. Why is it useful? Because now you don't have like matrices and so on. You can instead use functional relations and derive some differential equations, integral equations for these quantities. This is called actually, so if you rewrite this observable as a determinant of an integral operator, it is defined in some way. I don't want to go into very deep details. This is called the Fredholm determinant. And every observable that I will talk about has this nice Fredholm determinant structure. So how we can approach this problem? We need to introduce some other stuff which will be useful and not just some ad hoc things to define. So you can define with this integral operator the resolvent, for example, the resolvent function sandwiched by the position and one state, one Bessel function. And this will be quite useful since we know a lot the analytic properties of this function. I will denote this resolvent function by this qx function. What can you derive from the definition, from the integral operator definition of this function? First, you can derive some integral equations. This is very nice because actually it is not only one integral equation. It is an infinite set of integral equations, and you can solve them by some mathematical methods. And what you get is you get some ansatz for this resolvent function. The structure is quite important because you see you have some oscillating factors, also have this age xg. You don't know anything much about it, but you know that it is an infinite series of infinite series, exactly going with the same exponential corrections as our determinant, and also going with the powers of 1 over g. So if we can somehow determine these HKM coefficients, that would be nice. What is important is that we also have, somehow if you solve this integral equation, you see that the symbol appears inside the integral as well. So if you solve this equation, you will find that you will have this phi, the decomposition of chi, in the denominator. So somehow the zeros of this symbol function will appear as poles of, in this auxiliary resolvent function. So this is the first ingredient that we need. The second ingredient is also coming from these nice functional definitions. You can derive a differential equation for Qx, but what's important is that this differential equation now contains also our observable. So now we have something that we can effectively solve order by order. It's just a second order differential equation, so you can put it into mathematical solve order by order. But what's important is that this will give you relation between the observable itself and our newly defined function Qx. So this is what I wrote here. So somehow the coefficients in Q, H, K, N can be expressed in terms of the original problem, the coefficients in the original problem A, K, M. But this is not all. You also have some other relations as well. You also have an integral equation which also contains the observable and this Q function. This is actually, I think it's very nice that you have so many things relating these functions and everything, but this can also be solved order by order, just by hand or by Mathematica and everything, and giving another relation between these coefficients. So now you have basically two unknowns, HKM and AKM, and two equations. So that's in theory enough to solve everything. Of course, you need some boundary values as well to solve this, and it turns out that it's extremely hard at some point, at some exponential levels, but in theory, if you have these boundary values, like the starting value for AK at each exponential level, I think you could solve it only just by these ingredients. So this was actually enough to solve the perturbative part of the observable. Now we can go toward to see how we can determine the non-perturbative coefficients as well. So this is what we call quantization condition, but it has nothing to do with quantization. It's just a nice fact that since Qx is an entire function, it has no poles. So if we multiply this function with this combination which has Qx, as I mentioned, have these poles in theory at first guess. If I multiply with this symbol, which has zeros exactly in this location, in this limit, when we go to the location of these zeros, the residues should disappear. What happens actually when you substitute this value into this function? As you can see from the oscillating part, you will have exponential corrections exactly in the middle of the exponential corrections what we are looking for. One half level up from this part and one half level down from this part. So since they should disappear, you can match these coefficients, make them to 0, and what you get at the end of the day, what is the main message? That now you will have some very easy equations very simple equations to connect the exponential levels in H to the perturbative level of H. Now, since the exponential levels in H are expressed by the original AKN functions and the perturbative part of HK are expressed by the original AK coefficients, now you have like simple equations to express the relation between them. And actually, this is enough now to just put these locations and express the non-perturbative coefficients very efficiently by the perturbative ones. So this is the method what we used. So this is 4 steps. Each of them seem to be very difficult, but I put it in a flowchart. Actually, this is what we used in Mathematica, and it turns out that it can be used very efficiently. I mean, you just need to solve order by order this stuff. It do it very fast, and then just put it into the quantization condition, and you can get any corrections in 1/g and any exponentially small corrections. I mean, of course, it will take some time if you want it analytically, but we also made some numerical tests, and we get, I don't know, to 5 exponential levels, hundreds of 1/g corrections to thousands of digits of precision. So you can see here some results. By this method, we were able to reproduce some previously known actually resummable functions, which is nice. And here you can also see some analytical results for example, the octagon form factor or the n equals to observables. So what is important, so why we tested it numerically with such a high precision is that, for example, we wanted to investigate its resurgence structure. What is resurgence in a nutshell? I won't have time to go into more details. So if you have a function, actually an analytic function that have this expansion in 1/g, in sometimes, as in our case as well, you can get the coefficients. If you do perturbation theory or something, you can have coefficients with factorial growth. So here I put here some quite general behavior. So you have like if you investigate the behavior of these coefficients, you can also have some nice expansion in k, factorials of k, and some powers as well. But what is important, that if you want to resum this series, you find that it's divergent since the coefficient grows factorially. So what you can do, you can just divide them by this factorial. This is called the Borel transform. I denote this newly introduced function as Bs. This is the Borel function. It also has some inverse. So if you would have like not a factorial growth, but some nice convergent series, you can transform it to the Borel plane and then transform it back, no problem at all. This is the inverse transform of this Borel transform. What you see, what is important is that it is given by an integral of this Borel function. Okay, but since our coefficients in f grow factorially, it turns out that the coefficients in the Borel function will converge to somewhere, which will be, I mean, the series will be convergent, but only for specific values. What you get is that this Bs exhibits some singularities at some certain real values in the real line, in the positive real line. So it is not obvious how to do this integral, because it goes from 0 to infinity. If you just want to integrate it out, you will hit a pole at somewhere, which is not good at all. So you have some ambiguity. What you can do is you tilt a bit this integration contour a bit above the singularities or a bit below, but this gives you some ambiguity how you can transform back your Borel function. And actually, if you do this whole machinery more precisely than you can see here, you find that the ambiguity, the difference in these ambiguities will be exactly proportional to some exponentially small corrections. So these exponentially small corrections are necessary to kill these ambiguities to have some meaningful not divergent series. So what we did, so we had so many numerical values and so on. We checked that these resurgence actually work for these observables as well. So we connected these C0, C1, C2 coefficients to the next exponentially small corrections, and also checked whether resumming everything will give you or converge to the exact values. Okay, so this was the first class. I don't have so much time, but I want to talk about the second class a bit as well. This is from our third paper. And this is another class of these determinant observables. Here the structure is a bit more like difficult, because now you have a determinant of not just an infinite matrix, but a block, a 2x2 block of 4 semi-infinite matrices. So how you can compare to the previous one? In the previous case, you only have like, by tuning this L parameter, this curly R parameter, you only had either odd or even Bessel functions. Now you have some rotation in the subspace of even and odd Bessel functions. So by what you can find is that by fine-tuning this alpha parameter, which rotates you in these subspaces, you can get some other observables, like the cusp anomalous dimension of the octagon, or in case of this gluon scattering amplitude, some other alpha appears with rational R. So this is also exact for arbitrary Toft coupling. So we investigated this case as well. What you find is that now you have two exponentially small scale, this lambda minus and lambda plus. So we wanted to calculate or apply our previous method exactly to every order in lambda minus and lambda plus. We did the same machinery actually, just it was not like only integral operators, but 2x2 matrices of integral operators. It was a bit more messy, but everything worked fine as previously. So we were able to determine non-perturbative coefficients. So here the properties are not important. What is important that you also get factorial growth. So it is just a formal transseries, and now we can also investigate resurgence and anything. So it turns out that instead of investigating this F observable, it's more simple to consider its exponential, which I denote this by ZL. Not by accident, it's actually related to a string partition function in the dual theory or some other string observables. And the leading order is given by the semi-classical result, and you can get some subdominant saddle points, and this correction will exactly give you those corrections in the dual ADS string theory side. So we investigated the resurgence structure of these coefficients, and what we found is quite, I think it's quite interesting, because in case of this string theoretically meaningful function, you have some disappearance of the perturbative coefficients, and these arrows, what you can see here. So in the Borel plane, you have some certain poles at each level. This means that in theory, like lambda minus to the 0, lambda plus to the 0, the perturbative part could communicate to any of the non-perturbative coefficients, and also can communicate via 1, 0 and 1, 1 with 3, 2 or anything. So in general, you should have some nested structure of resurgence in this case, especially since you have two exponentially small scales. But it turns out that not everything communicates with everything, and we found this nice structure. We don't understand it yet, so it's a further plan to see what is the resurgence structure behind. I mean, not the resurgence structure, but the whole mathematical stuff. Why this happens, and also what is like the string theory meaning of the disappearance of some coefficients and the relation between them. So I want to conclude my presentation with this feature. So this is for the tilted cusp. Here we plotted the the weak coupling expansion, the strong coupling expansion, and the exact results coming from matrix truncation for different values of parameters L. And if you remember the first, the sketch on the first or second slide of my presentation, this exactly shows that with these non-perturbative coefficients and strong coupling, we can go very, very close, like with 10 to the minus 20 to the exact results. So this is what I wanted roughly to tell. So we investigated some observables in n equals 2 and n equals 4. We investigated their strong coupling. We gave a systematic method to get the coefficients to arbitrary order, also in 1 over g, also in the exponentially small ones. We did some numerical verifications, checked the resurgence properties. So what we can do, we don't know what is the dual description in each of these cases. How can you get these coefficients, for example, from string theory calculations? We can also investigate some other limits of the octagon form factor, also investigate the resurgence structure a bit more deeper. There is a whole mathematical machinery behind that, what we don't really understand yet. And also there are other theories, for example, the ABJM theory, where some Fredholm determinants and these resolvent functions seems to be quite useful. So thank you for your attention.
Okay, we have time for a few questions. Any questions? Right there in the middle.
Thanks for your nice talk. I want to ask a question about the last two slides about the partition functions. Yeah.
This one? Yes.
Yeah. When you say compare to the string theory side, that's a flat space string or ADS string?
ADS.
Okay, but I don't think people have the real ADS string theory.
No, that's what I mean under we don't know what are the dual meaning of this graph, or maybe I don't understand the question correctly.
So this is a prediction of what this string theory in ADS should be.
Yes.
Okay, thank you.
I mean, there are some certain cases which are more simple, like some Wilson loop on the n equals 4 side, where it was actually done. I mean, there they were able to calculate the string theory correction, the exponentially small correction, and there works. We checked that, but that is very simple, and that's all we have right now. So yes, it's a prediction more like.
Okay, thank you.
Thank you.
Koya? You have a booming voice. You can probably, you don't need the mic.
So what you actually call cusp is not a cusp, it's like just phi square coefficient of it, right? Or theta square coefficient. What you call cusp? Is
the cusp anomalous dimension. I mean, like if you renormalize.
Yeah, but it's not the function of theta. It's just theta square coefficient. That's Bézier over Bézier. What you probably speak about, right? Bézier I over Bézier I. So my question is whether you can also pack phi to the 4 coefficient, which is also known analytically to any order. Well, analytically the function of G into the Fredholm determinant. Because that would be highly non-trivial, I guess.
Yeah, sure. I couldn't comment on that right now. I mean, it's a good question.
All right, let's thank Marcel for this talk. I'll give you 10, 5. Okay. All right. Yeah. So our next speaker is Benjamin Bassot, and he'll be talking about cornering correlation functions with hexagons.
Thank you very much. So, well, I'd like to start by thanking the organizers for having me here. Of course, it's a great honor to be invited to talk at IGST, and it's also a pleasure to be back in this wonderful city. So today I'd like to talk about some work in progress with Thiago Fleury in Brazil, Erkan Kalous, my student from Paris, and Didier Nasserman, about behavior of correlation function in planar n equals to 4 superior mills using our favorite method, which are hexagons. So we'll say a few words about hexagons, but very quickly. And hopefully trying to say something about some general properties they may have at finite coupling in some kinematics. Okay, so I try to put all of this in order. But I'd like to start with some disclaimers. So this is really a work in progress that we started not so long ago. So it does look a little bit like that at the moment. So if you don't know this painting, this is House of Parliament. I guess if you don't know this painting, you don't know this is House of Parliament, probably, although it's a famous painting. And well, this is where we stand at the moment, so don't be too tough on us if it is not super sharp. I believe that with more time and more integrability, we'll be able to say something clearer and hopefully find some beautiful Gothic architecture behind this painting. Okay, so here I start with a few slides of motivations. So the overarching goal, of course, is to try to understand this proposal by some people in the room, including Shota, Komatsu, Thiago, many others, for studying correlation function of single trace operators in the large n limit of n equals to 4 superior mills. So I say large n because I will be talking about planar limit mainly, but there is also, as you probably know, a very nice story about 1/n correction. So it's really a technique, a tool that builds on the string theory intuition that we can think of large n diagrams as being organized into topologies at large n. And the technique is very powerful in the sense that it is very flexible and allows us to essentially cover a lot of things. Whether we can compute concretely is still a very open problem, and this is essentially what we are trying to understand here in some situation. And the basic idea, so it's called hexagonalization. It means essentially putting a hexagon together. And the idea is pretty simple. It is based, again, in the strict large n limit when we consider only the spheres. It's based on the idea that planar spheres is a bit redundant, I guess, anyway. The spheres, which are punctured by a single trace operator, can be triangulated using hexagons. So here is a cartoon, the simplest example of hexagonalization that we may have for a 4-point function. So each operator here, single trace, is represented by a spin chain state, or a string state, if you want, 1, 2, 3, 4, which has, well, again, the usual single trace operator, half BPS operator made out of product of complex scalar fields. And so they contract with each other, like with contractions. There can be many other stuff on top of it, like gluons. But the idea is that essentially what we will get is a triangulation of the object. So here we get a triangulation with 4 triangles, 3 in the front, 1 in the back. And because each operator has this thickness, intrinsic spin chain thickness, there is actually a piece of the apex here of the tip of the triangle, which is replaced by some new segment, and that gives us what we call a hexagon. Okay? But so the hexagon has 3 sides that live in space-time. This is a triangle, space-time-wise. It also has 3 corners which live in a different space. Put together, it's an hexagon, but graphically, it's more like a triangle if you want to reduce the puncture to what they should be, which is just a point. So why do we like this picture? Because, well, first of all, we feel like it has something non-perturbative in it, like it should be applicable to any type of, the sum of any Feynman diagrams in this theory in the planar limit. and besides, thanks to integrability, these 25 years of integrability, 25 or 20? 20 years of integrability, 23 maybe, I forgot, has allowed us to develop powerful techniques, including this hexagon construction. And so we believe we know these hexagon form factors exactly as function of the Taft coupling. Okay, so these building blocks, these patches here that we want to put together, we think we know them at any value of this Taft coupling constant. The problem we are facing now, it's not really a conceptual problem, but it's a real technical problem, is to actually glue these things together. Because the rule for gluing entails inserting a complete basis of state here along these edges, which we call mirror cut of the triangulation. And there are many states we should sum over. These mirror magnons can propagate from one triangle to another, or from one hexagon to another. We should sum over them. And although there is some beauty attached to it, like some supersymmetry that is left and so on, turns out to be extremely difficult to perform these sums in practice. Okay? So what we need are techniques to figure out what we should do, also maybe some roadmap for where to look at simplification and how they could come about. So one first simplification that have been noticed already a few years ago is that we can somehow make our life simpler if we consider large charge correlators, or if you prefer disk correlators instead of the full clustering correlation function. So the idea is to just look at one part of the diagram that I was writing before, so just say the front or the back. Imagine we can, for somehow, by tuning the charge of the operator, engineer a configuration that is such that we get a lot of stuff here on the boundary, which make it impossible for the magnons to propagate from the inside here to the outside, and so isolate some piece of worldsheet of a form of a polygon that we can study more quietly using hexagons. Okay? So by doing so, we are killing some cycles. Cycles are bad in practice. They're often source of complications. It's not necessarily true for the hexagonalization for protected operators, but yet it is definitely a complication in the sense that we get more hexagons to put together. So no cycles here in my talk, just some hexagons that we put together, or if you prefer triangles, such as to form some big polygons. Not necessarily super big, but let's say bigger than the starting point. And this also, if we succeed to understand maybe the structure, this may be also building blocks for correlation function of short operators, assuming we can then start adding stuff on the boundary, put things together. It may also be part of something that some of you might like, which is correlation function, on a defect, like a Wilson line. So for that, you will have to put actual dynamical boundaries here, like the Wilson line, that will interact with the inside. And so that will change a bit the physics of the problem, but this is still part of this calculation is relevant for that defect correlator. Another reason to like this object is due to a proposal by Frank and Simon, which is that there is some evidence, I would say important evidence, that this object can also be interpreted as scattering amplitudes. So scattering amplitude in some sort of dual space, and for a theory that will live on some Coulomb branch. I will not enter into the details, but this is something that we should keep in mind, and Frank and Simon are providing evidence for that. that there should be some connection between this object and scattering amplitudes. Which connection precisely? Well, that's something maybe we should work out and make more precise. And again, this is a toy model for exploring this resummation because there are much fewer obstacles, I would say, or channels. Okay, so here's a prototype. So we heard a little bit about it already in the previous talk. The prototype of this object is a large charge limit of the 4-point function. So this is this limit where the 4-point function factorized into 2 octagons, which was introduced by Frank and further studied by a lot of people. And what is extremely nice about it is that it can be computed exactly. So everything I told you about this summation of states, mirror states here, end up essentially reconstructing a freedom determinant of a Bessel kernel, precisely the type of determinant we heard about in the talk by Bessel. So this is very encouraging, you would say. This is showing that there is a lot more to say about this hexagon approach. There could even be something that does not care anymore about hexagons, that builds essentially on some functional property of this determinant. So let's be optimistic that such a thing may be found in the future. But at the moment, I would say that it's extremely hard. There is a gap, a serious gap, between this computation for the octagon and the computation for the higher polygons. Okay, so it's extremely difficult to generalize this analysis to higher polygons, even the simplest ones that will be a 5-point function. Okay. I should say that there are nonetheless some very important results that have been obtained over the years, and which indicate that there are things that want to be found there. It's not just hopeless, of course, but there is still a gap in practice. So in order to learn a bit more about what type of difficulty we have here, we may try to look for more exact results. Some of these results, that exist when we go to a particular kinematics. So instead of trying to do generic kinematics, which may be too ambitious as a starting point, we may try to find some corner of the kinematic space where things want to simplify and perhaps tell us something about the resummation technique we should find. And here again, there is some indication we can get from the octagon and from the paper by Frank, which is about this null square limit, where the two cross ratios of the 4-point function are going to 0 simultaneously. So this is a limit, again, where the polygon literally becomes a null square. Okay. And Frank observed through many loops, and later on, people here proved it, that the log of the correlation function is quadratic in the logs of these small cross ratios. And is entirely controlled by a single coefficient of the coupling, which is this octagon anomalous dimension. On top of that, this octagon anomalous dimension is a very, very gentle object, I would say, since it admits an extremely closed expression, which is given here. Okay. So this is evidence that some nice thing may happen, and also even some bonus, I would say. But of course, it's still the octagon, and you may think that, okay, you say that it is extremely simple, that it's not a good example, I would say, for the rest. But yet here there is something that is also resonating with some behavior that was observed in the context of scattering amplitudes, which are not known to be especially simple in this theory, although they are subject to important simplification. Which indicate that we may believe or may expect that this type of behavior will generalize to higher point functions. And here, this is what I would like to explain in this talk, which is discuss this generalization by also mentioning the links with what we called in our previous paper with Lance, Andy, and Yorgos, origin limits of scattering amplitude, which is a generalization of these light-like limits, if you want. Okay, so some particular corner of the kinematic space where we should expect and we should be able to prove that correlation functions simplify and take a very pleasant form. Okay. So here's a rough plan. I try to follow it. So I will start with some kinematics. Then I will explain what we've been able to do. So this is just about trying to classify a little bit, what type of limit are we talking about? How many are there? Just get some rough idea of what they could be and how to describe them. And then there will be some hardcore integrability, which I will try to keep as light as possible, mainly because we don't have so much result yet. And of course, conjectures, which are free and always great to make. And also some other conjectures. Okay, so what type of origins are we talking about here? So what type of limit? So here it's important to say from the very beginning that I'm going to stick to a particular subkinematics, which is a 2D kinematic. So for 4-point, it's not really a restriction. We can always put 4-point in a plane. For higher point function, it is a huge simplification, especially at the level of the hexagon construction. And we are going to make this assumption here, by keeping in mind that there may be an even bigger world outside there waiting to be explored. And in 2D, we have a lot of techniques for describing the geometry. Here I'm reviewing some basic facts that should resonate. So in particular, since we are in the plane, we can go, to spinor variables. Or if you want to point on CP1, the projective plane, and describe this way the left and right moving coordinate of our vertices. So we have vertices in the plane. They have ZZ bar coordinate, if you want, or XX bar coordinate. And we can describe them in terms of spinors, modulo some projection symmetry that allows us to fix the North Pole, essentially. Equivalently, we may package all of these guys, the left or equivalently the right part, inside some 2×n matrix, which is just some Grassmannian. Again, modulo this torus action that is just this projective redundancy, which here I use, for instance, to fix every top here to 1, except this one, which you should think as a point at infinity. So this is a point at the origin of the plane, if you want. This is a point at infinity. This is just 1. And these are the other points, which I'm putting a bit randomly. So we get 2 copies of these spinors. And we need both of them to reconstruct the actual distances in the problem. So the actual distances are the product of these angle brackets, 2 types of angle brackets that we get by just doing spinor contractions here. Okay. So I should say, the conformal group here is acting just as SL2 times SL2 on this object. So this is the great thing about these variables, which is that we can just linearize the action of the conformal group on them. So beside this, natural embedding or representation, there is also another important thing that comes with our triangulations, with our hexagonalization, which again start off with a triangulation, which is that each triangulation comes with a natural set of cluster coordinates, which serve precisely to, they just serve to parameterize the geometry up to conformal redundancy. And in this construction, each coordinate is associated with a cut or chord in the triangulation and is given by a very local rule. So you just look at which chord you are talking about, and then you construct the cross ratio, using the other element of the triangulation that's around it. Okay, so here, for instance, the variable ZAB, the cluster coordinate associated to A and B here, this chord, is just given by this product times this one divided by this one and that one. This is just this cross ratio here, if you have never seen it before. So actually, these are natural coordinates in the hexagonalization. They are this is what determines the weight of the mirror magnon. So when we use hexagonalization, for every cut, as I say, we have a sum of our mirror magnons, and each one of these mirror magnons is weighted by something which is related to this Z. Okay, so when we change the geometry, we change the way we weight these magnons, and there are especially some limit when Z is small, for instance, where the weight is very negligible, so we control very well the sum of all the magnons. There could be other regime, like when Z is large, where we need to resum or do something to understand what is happening, okay? This something that we may want to do in some situation is a mutation. So this is a transformation that exchanges essentially Z small to Z large, and it maps cluster coordinate of one triangulation to cluster coordinate of another triangulation associated with a flip. So this is a basic example where you introduce a coordinate for this set of chord here. You do a flip, which is just a change of triangulation, and you get new set of coordinates, which are related by some algebraic relation. Oh my God, 10? Okay, so this is all very basic, you agree? So this is the exchange graph of the cluster algebra. We get some A1 here, we get some A2, which is a pentagon. And what is important is that we can think naturally of the kinematic space as something that will fill the inside of this picture. So in particular, here this mutation will be like at the boundary of the picture, and the physics inside will be called the positive region. So a cluster origin is something that we can identify with a point at this boundary here. Okay. So, and this is at the boundary that we expect singularities to develop typically. Inside, everything should be smooth. So there is another way of thinking about this point at the boundary, which is quite nice and which is based on this binary geometry. So in this case, we should define some cross ratios by using a cross ratio which are associated with chord, again, by using this formula. So in this case, we take point at the boundary of the polygon, and we construct this particular quantity. Doing so, we get too many cross ratios. It's overcomplete. And we find some elegant constraints on them, which relate the cross ratio of the segment ij and the product of all the cross ratio of the segment or chord that intersect ij. Okay. So why is this relation very important? It's important because if we now go to the boundary by sending a u to 0, we find that all the other u which are incompatible or crossing that chord are going to 1. Okay. So in particular, vertices on the boundary will correspond to the choice of a binary sequence in which n-3 cross ratio vanish, so they go to 0, and all the other ones are going to 1. So as I say, we get left and right geometry to take into account. The physical cross ratio are the product of the two. So in practice, if we want to maximize the number of cross ratios that are going to 0, which is something that we want to do as a simplification to begin with, we should choose for the left and right geometry two triangulations which have no chord in common. Okay? So this is what I will call an origin here. So here's an example, for instance, where I have like a chord 1,3 and a chord 2,4 here. So they clearly cross. So they will maximize the number of u going to 0, and indeed we get 2u going to 0 here. For the 5-point function, I can make this choice for the left part and the right part. And what I will find is that I will find that 4 cross ratio are going to 0 and 1 is going to 1. There is always one line here, which is not, for instance, 3, 5, which is neither a chord here nor a chord there, and which has to go to 1. Okay. So at higher point, we usually get more possibilities because we can choose these two triangulation in many different ways. That gives rise to a lot of interesting behaviors that of origins, of candidate origins, that we may want to study. Here I'm only giving 2 as an example, but there is in principle more that needs to be classified. So what do we want to do next? So we have these origins, and we want to explore how the correlation function behave in these limits. This is something that proves to be very difficult. If we have a big polygon with many origins, we need to explore them all. All of them will correspond to various behavior in terms of the z coordinate, which I introduced at the beginning for a given triangulation. So in general, it's hard to do, but at one loop, there is a nice formula that was worked out, and which allows us to essentially express any computation in terms of block-Wigners. And there we can just take our origins, plug the behavior in terms of the z, so we have to scale the z in some limit, in some way, to get to the point we're interested in. And then check that this is actually becoming quadratic in logarithms, as we will expect from the generalization of what was observed for the octagon. So there is more we can do in principle. So here I will go a bit fast because I'm already late. So we can use the hexagons at higher loop to try to do some computations. This is a tough computation, but we can develop some techniques, some trick, and verify in particular this result of rank and so on, that the 4-point function is controlled essentially by 2 coefficients, a simple function of the coupling. And then we, oops, okay. Anyway, forgot Okay, so this is showing that what we expect is, of course, there for 4-point functions. That was our inspiration. Then we can go to 5-point function and start observing what happens. So we can do this, try these techniques of simplifying the sum over the mirror magnons in the limit we're interested in, see what comes out. Of course, this is in practice relatively difficult. But again, this is something we can do up to a certain number of loops just by turning the crank and sweating a little bit. And so far what we observe is that indeed the result wants to exponentiate, and the exponent is quadratic in the logarithm. So we pick an origin. This is defining a certain limit. And then when we analyze what happened in this limit, we indeed find that the result exponentiates and that the exponent is quadratic. And the structure is, again, very similar to the origin in scattering amplitudes. And so we may expect to be able also to accommodate it under the umbrella of some big conjecture. So what is this conjecture? So this is where we started to speculate a lot. But of course, after speculating, we'll have to do calculation. So here I'll be fast because it takes a while to understand this formula. But what it expresses essentially is how to construct a quadratic ansatz for this log of the amplitude in any origin limit in terms of two building blocks. One is this tilted cusp, anomalous dimensions, that was introduced in the previous slides, and which was also appearing somewhere here for some specific values. And the other one is what we call the string integrand. This is something that we can construct in principle from some sort of string theory description as strong coupling, which is based on the TBE. What? There is an entire slide here. Okay. That's anyway, let's keep going. There is a string integrand, which is based on some potential minimal surface description that we are still looking for. We don't know how to characterize it for a string theorist, like tell what he should be computing, he or she should be computing to get the result. But we can use integrability to cook up the answer. Okay? And from there, we can read off this important information about the string integrand, which we can put under this integral transform together with this tilted cusp anomalous dimension, which was synthesized here to this formula, and get the answer. Okay? So I told you that this will be a bit impressionistic. Yes? So there's some hole in the description. Anyway, the end result is this. Okay? Log of the object is the sum over some alphas. Which alphas? Well, you need the TBA description to figure out. Some polynomials, no coupling here, just string theory prediction, and this generalization of the BES cusp, this tilted BES cusp anomalous dimension. Again, everything in principle is predicted. I just clearly don't have time to predict it now. But here is, for instance, what we got at 5 point. So we get this funny alpha, pi over 12, 5 pi over 12. Who can guess this? But magically, and also some polynomials, this is just to show that there is a bit of calculation behind that. And this is actually matching through 3 loops, the data that we had, and we are now pushing it to higher loops to make sure that everything is safe. Okay. So anyway, there is more to say, obviously, but it's time to conclude. So the planar disk is an interesting area, I would say, for studying resummation techniques at the level of the hexagons. Construction through this origin limit. So there are some important simplifications here that I've mentioned, which make it easier compared to the problem we had for scattering amplitude. One of them is that we have a simpler cluster algebra. We have these U coordinates, which are extremely nice to label the point at the boundary by some binary sequence. Everything is very transparent, and again, easier to depict and think about. And so the next step is to study how the correlation function behave in this limit, and in particular in all these origins. So for what we can say, what we are seeing is consistent with scattering amplitude behavior. We do get this nice exponentiation and quadratic in log behavior. And it is also consistent with an all-order formula. What we don't have yet is a complete dictionary and a lot of evidence, I would say proof maybe, that this is correct. So because as you go to generic n, you get plenty of origins. you need to, put them in correspondence with some TBA, some saddle point of the TBA equation, and show that this is going to reproduce the actual result. So this is where we need to do some more, I would say, realistic job, which is to try to prove. I don't know how much we can prove here, but we can certainly test many things and possibly also bootstrap some part by some consistency condition. There are, again, some other limits which are worth considering, which are not exactly origins, but which are closely related to them, which are this null or light-like limit, and some relation to pentagon OPE, but that I will leave for another talk, I guess. Thank you very much.
Okay, we have time for some questions. Well, since you felt rushed, you have 5 minutes. Would you like to talk about something in a little more detail?
I'm not so sure. That's weird, actually. No, I don't really. Well, no, I think it's good like that.
Okay, Carlos.
So when you do the amplitudes in the origin limit and you see this many gamma alphas appearing, and when you see here like a large charge, do you see the same times of gamma alpha? Do you see different times of gamma alpha? For example, 6 points?
Yeah, so the gamma depend on the saddle point. In fact, this is really the string theory saddle point that determines which alpha will show up, or which alpha will turn on and which one will not. And the TB equations are different between the two problems, so they are going to predict different behavior. What I can say is that this gamma oct appears quite often, but not always, not all the time. And also at higher n, it often appears with many other alphas, not just gamma oct. So this is somehow related to what is written here, which is that the problem is not just controlled by gamma oct. Naively, there was this idea, okay, maybe you replace gamma cos by gamma oct, and you understand the general structure of these limits for this new kind of amplitude-like object that we have here. But the structure is less universal, is more complicated. It involves many of these gamma alphas. And again, the alphas depend on the limit and the number of points and so on. And why is it so? I don't know. I don't have a general understanding. At the very best, we have this conjecture. If correct, it's predicting the result. But now, someone has to analyze it.
Okay, so if there's no more questions, let's thank Benjamin.
All right. So yeah, let me start by thanking the organizers for this very nice conference, and of course also to give me the opportunity to speak to you today. I'll talk indeed about Jordanian twisted string theories and Jordanian twisted spin chains. Will be based on work that I did over the last few years with Ricardo Borsato in Santiago de Compostela, and then also work that appeared today on the archive with my student Adrien Molin, who is also here, and he will also have a poster tomorrow. So, because I'll be talking in these 30 minutes about these two different topics, I hope I can still give you some interesting facts about them, but any more discussion, if you're interested, I revert to the poster. I'm sure that Adrien will be happy to discuss it. So yes, the motivation of my work stems basically from looking at deformations of the ADS-CFT correspondence and using integrability to study those things. In particular, there is in fact a very nice, simple algebraic realization of deformations of the integrable framework, of the integrable hop framework, which is known as Drinfeld twists. So I'll explain what they are during the talk. And basically what they do is like twisting your universal R matrix in some nice way, such that the properties of the Hopf algebra will be preserved. So in contrast to Eddie's talk of this morning, we will still have like Yang-Baxter equations and stuff like that that is valid here. What I'm interested in is applying these type of things to the case that we all know and love very well, which is the ADS-554 correspondence in the planar limit, where we have this nice triangular structure of theories, where on the one hand side we have a string theory propagating in ADS-5S5 spacetime. Then on the other hand, we have this highly symmetrical gauge theory, which is NS4 superangles. And then underlying to that, as we all know, is some PSU2,2/4 invariant spin chain that encodes the integrability of these two models. And so, as you know, they're extremely symmetric. So we have PSU2,2/4, so we have some conformal subgroup. So the gauge theory is some CFT. We also have maximal SUSY, and we have integrability realized through Yang. So the question that I want to ask in my work is, can we sort of twist this triangle with these Drinfeld twists, and in that way study symmetry breaking effects in theories like quantum gravity and QFT models, where we still have exact techniques in principle from integrability. And now there is some nice conjecture about the modification of the integrability framework by these Drinfeld twists, which was formulated in 2015 by Stijn van Tongeren, which is that at least at the string theory side, we have a deformation of this model, which is called, by the very creative name, a Yang-Baxter deformation, and maybe we should actually call it a classical Yang-Baxter deformation, where, so as I said, the target space in which the string gets deformed, in which the string is propagating, it will be deformed. And it is done, the deformation is done by some object, which is some classical type of R matrix. And then in the other corners, we have this Drinfeld twisting of the quasi-triangular Hopf algebra of the spin chain. And on the gauge theory side, the idea is, or the conjecture is that the field product of the gauge theory gets deformed through some star product, which is also realized through a Drinfeld twist. And in this talk, specifically, I will talk about Jordanian deformations, which are a part of Yang-Baxter deformations, and I will focus on the string and on the spin chain side. Okay, so yeah, the first part will be on the string world sheet, where I'll talk about the Lax and the S matrix, and then I will go to the spin chain. So first, let me tell you what the definition is of a Yang-Baxter string sigma model. So there are some particular integrable deformation of a two-dimensional sigma model, so the world sheet theory, which has some isometry group G, which in the case of ADS-5S5 is PSU2,2/4. And it has this very particular action, so we know precisely what the two-dimensional action is. The precise form doesn't really matter here, but I just display it.
it is in principle just some deformation of a Green-Schwarz superstring. And a deformation is governed by this object eta and r. So eta is just a deformation parameter, and r is a particular operator. And then I should also tell you that G, which will come up later also in the talk, G is a collection of fields, some group-valued collection of the fields of the worldsheet. But so this, the important bit here is this operator, this classical R matrix, satisfying a bunch of properties. So in particular, it satisfies a classical version of the Yang-Baxter equation, which is this line here, and it's also antisymmetric with respect to the metric of the supergroup. And also some unimodularity condition, and those conditions combined will ensure you that the two-dimensional worldsheet theory is still classically integrable, so I can write down a lax connection for you. And also the resulting background in which a string is propagating will be still a solution of the type 2B supergravity equations of motion. So it will be some complicated solution, but it will still be a solution. And now all of these sort of properties, what is interesting is that they correspond to Drinfeld twists, classical Drinfeld twists, which are connected to the identity. So I have this object curly f, that is the Drinfeld twist, and it's connected to the identity through this R matrix in here. And interestingly, in the case of PSU224, we have a whole plethora of possible solutions to these conditions. And these have been classified in these two papers here. So there's a huge family of possible integrable deformations that you could study in principle. Some of them are actually quite well known to you. So there's specific Yang-Baxter deformations which give you the backgrounds that have been studied a lot, so like the Lunin-Maldacena background. Also Schrödinger spacetimes are realized as Yang-Baxter deformations. And then there's a whole bunch of other possibilities which haven't been studied. And I'll try to go quick, but basically they're sort of distinguished by, in three main classes, and they're distinguished by the subalgebra, which is the image of this R matrix that is minimally two-dimensional, so it's spanned by at least two generators of PSU224, so T1 and T2. And then you have these three classes where either the subalgebra is abelian and the generators are Cartan generators, so they are diagonalizable. In that case, we say that they are called, well, we call them diagonal TST transformations. At the level of the worldsheet, you can actually understand them as TST, so T-duality, shift T-duality transformations over this commuting subalgebra of isometries, this abelian subalgebra. And in the second case, we still have an abelian subalgebra, but then one of the generators may not be Cartan. This is, of course, possible in PSU224. In that case, we will call it a non-diagonal TST. Basically, the classical Drinfeld twist that is associated to it is non-diagonalizable. And the final class that I want to study are called Jordanian deformations, where the subalgebra is non-abelian. It is some type of SL2R subalgebra in PSU224, where the T1 generator is the Cartan of SL2R, the H, and the other generator is the raising or the lowering operator or generator of SL2R. And what is nice about them is that they have a classical Drinfeld twist, which is diagonalizable, and that sort of, I will not be able to really tell you why that's nice, but basically it should allow a nice treatment of the integrability methods. So just to complete a bit the picture, so I told you have this Lunin-Maldacena, which is some diagonal TST, and we also have other cases. What do we know at the gauge theory side? So we can take these two generators, these commuting generators, to be commuting generators in the isometry group of the sphere in SO6. So then we're not deforming the ADS space, and we will have a marginal deformation of NS4. The other possibility is that you take abelian generators where one leg is in the ADS space in SO2,4 and the other leg is in SO6, or you have two legs in SO2,4, and in that case you'll be deforming the space-time symmetries of the gauge theory, and that introduces to you some non-commutativity between the fields. So that relates to these non-commutative star products that I mentioned earlier. And then for this SL2R subalgebra, the Jordanian case, it's really totally unexplored terrain, what happens there. But also here, there should be some non-commutativity. Okay, so now let me just focus on very particular Jordanian deformations. As I said, there's many possibilities, but there's one that I think is interesting, which is one where we have the Cartan generator of SL2R, which take this form in terms of the conformal generator. So here we have the dilatation operator and then some boost generator. And then the root of SL2R is some null momentum combination of the momentum generators that we have here. And this is a case that will give you a constant dilaton. So in the other classes of Jordanian deformations, you will always find non-constant dilatons up to this nice structure and possible generalizations of this one. So that's the one I will be focusing on, and that is also the one that has been studied from various angles before. Now, what is nice about this one as well is that it has an interesting symmetry structure. So the residual symmetries of the sigma model and the ADS in the ADS5 space I've listed down here. So there's like 5 generators that remain after this deformation. And as you can convince yourself, there's some SL2R subgroup and 2 central elements. And this SL2R subgroup is also called a Schrödinger algebra, which is relevant for studying non-relativistic CFTs. So in particular, we don't have like a relativistic SL2,4 CFT anymore, but we still have some sort of non-relativistic version of that, which is surviving here. So we have this boosted dilatation operator, which will define for you some non-relativistic scaling symmetry. And then we have these other guys, which will define for you the descendants of the non-relativistic operators and also a state operator map. Okay, so then what will be important throughout the talk is the existence of the Cartan subalgebra in ADS, in this ADS space. We have, as in the usual case, we will have 3 Cartan generators, but they look very different to usual. So we have always the E generator, this raising operator that will be present, and it will be defining for you some charge, which is some null momentum M, and this M will continue to appear throughout the talk. Then we also have some rotation, this J12, which will define some spin in ADS, and then we can choose 2 elements of SL2R as a third Cartan element. We either have a timeline generator, which is this guy, which will define an energy for you, and then finally I also have a radial generator, which will define this non-relativistic scaling. And they are related through the state operator map in this case. Okay, and then you also can write down the type 2b supergravity solution in terms of those isometry relations. So now that I defined the model, let me talk a bit about the possible integral structure of these cases, and I'll start with the S-matrix formulation of this guy. I won't have a lot of time to give you all the technical details about this thing, but basically the point is that because we're severely deforming the space and we're left only with a specific Cartan subalgebra, we cannot do the usual identification of the asymptotic states that will be scattering in the, that will scatter through each other. And you'll have to do another type of gauge fixing, so a specific light cone gauge fixing that will change your structure. But let me just mention that the solution that you take to do the gauge fixing will be this particular type of, you can take the simplest possible solution will be of this form, where we turn on some energy as well as this null momentum M and an angular momentum in the sphere. We leave the spin of ADS, we can turn it off, and then we will find some, the Virasoro constraint will relate these charges to each other in this particular way, which is, if you're used to it, is just a deformation basically of the BMN or BPS operator where the energy is equal to the angular momentum. So at some large values of the angular momentum, we'll just have some combination here, a deformation of that with this momentum charge. Okay, and so we use this energy to do the gauge fixing. As I said, you do a different type of gauge fixing. You'll find some different worldsheet Hamiltonian than in the usual case. So you will have some symmetries of that gauge fixed theory, which will not be the usual PSU2/2 squared, but there will be some different symmetries. And in fact, the symmetries that are surviving, they contain this H and this E that are defining the Jordanian deformation. So in principle, you could think of like also twisting the S matrix of this gauged fixed theory through some type of Drinfeld twist, as I said here. But so this is sort of like the expectation of what should happen. But if we would start to like shut up and calculate and see what the S matrix actually is, we run into some strange features. So we take this gauge, we find the perturbative Hamiltonian, we look at its expansion in the asymptotic states, where we have this cubic Hamiltonian contributing as well as higher order terms. And then we will find that we'll get some very nasty dispersion relations for the excitations, so they take this form. They're non-relativistic. And that means that you cannot just use normal kinematic rules for them. And in fact, you'll find that this cubic part of the Hamiltonian will not just disappear because of this non-relativistic dispersion relations, but it will actually contribute physically to the scattering of the S matrix. And we find in particular two nasty production processes that involve massive asymptotic particles. And as you, I'm sure, very well know, this is quite not nice because it means we have inelastic scattering at tree level, which is violating the usual axioms of S matrix integrability, or in principle, it's just jeopardizing the methods that are based on factorized S matrices. And it's also like sort of questioning what is happening to the Drinfeld twisting, because usually the S matrix in the sigma model is the first signature that you have this R matrix appearing. Yes. Higher order in what? Yes, yeah. I mean, I would expect that I already at tree level I should have no production process, right? Yeah, well, maybe I can talk about that later. Okay. Oh, okay, I see. Yeah, okay. Well, yeah, no, I'm not, I don't think so. I don't have a compelling intuitive answer for now, but it would be quite surprising to me, actually. But, okay. So, yeah, anyway, what I just want to say about this is that it's like a sign of that the asymptotic Hilbert space is kind of weird, and maybe particle number is not a good conservation quantity, conserved quantity. And it's also something that we see signs of in the spin chain language. Yeah, so all in all, I think, well, so it's the S matrix formulation is a bit unclear, but what the connection to the Drinfeld twist is kind of nice in terms of the lax integrability, which I'll just briefly discuss right now. So we have these two classical lax descriptions for these Yang-Baxter deformations and also for Jordanian ones, where we have sort of two pictures. On the one side, we have a deformed interaction picture where the Hamiltonian is deformed through this eta R object, but the fields of the sigma model are still periodic. And then we can derive some lax connection of that, which depends on this eta. And on the other side, we have an undeformed interaction picture, but the fields, the deformation gets completely transferred to a twist in the fields themselves. So here we have some twisted strings propagating in some undeformed space-time, and here we have some closed strings in a deformed space-time. And the mapping between the two is done precisely by some type of classical Drinfeld twist, which is this F here. In fact, you can show that if you look at the sigma model monotomy, the generator of the conserved charges, it is classically Drinfeld twisted in the following way. So you take this monotomy object, which is this path ordered exponential of your deformed lax connection, and you see that you can sort of strip off the deformed part in terms of like some overall twisting of the undeformed monotomy object here through this guy F that carries the deformation. We found in this paper in 21 here that it is indeed of this classical Drinfeld twist form, so it's connected to the identity again with the same object. And then for the abelian or the Jordanian deformations, we were able to write down explicit expressions. And for those that are familiar with it, in the abelian case, we really get some abelian Drinfeld twist, which is also known as a Drinfeld-Reshetkin twist. And then for the Jordanian twist, we get a structure that is also very similar to known Jordanian Drinfeld twists. So yeah, that brings up a sort of first connection between the string theory and the spin chain, where the string is twisted with this type of object. So now let me go to the spin chain formulation of these models through this Drinfeld twist. So now I can be a bit more precise about what they mean. So as I said, I'll be looking at this minimal Jordanian model that is non-trivial in an SL2R sector of PSU224. And in that case, the relevant spin chain is the Heisenberg XXX spin chain in a non-compact representation of spin -1/2. So it has some Yangian SL2R related, realized through some co-products, and has some R matrix. And in this, for this particular case, the R matrix in some representation takes this form here, where we have the generators of SL2R acting on physical spin chain sites through some differential operators in some continuous parameter Z. And so the wave function is also some depends continuously on this parameter. Now you can Drinfeld twist this theory, and that specifically what you have to do in order to preserve the co-cycle condition is you need to have some object that satisfies this. What you need to do to preserve the quasi-triangular Hopf-algebra or the R matrix integrability is that you need to have an object F that satisfies this co-cycle condition. And in the case of the Jordanian Drinfeld twists was done by people like Coolidge and probably also many others. The form of this Drinfeld twist has this exponential and also this log term that also similarly was appearing here at the classical site. Where we have this, again, this Cartan of SL2R and this raising operator of SL2R, and now my deformation parameter will be psi, which is some real deformation parameter. And then you can show that you can actually twist the Hopf-algebra, so you get some twisted co-product, some twisted R matrix, and you'll just have normal Yang-Baxter equations and RTT relations, etc. Now, importantly for analyzing this type of model, and especially the spectrum, is looking at the symmetries that are the residual symmetries of this system. And for the level 0 or the SL2R generators, you'll find that the only manifest symmetry is realized again through this E operator, which we also had at the sigma model side. It's also always a residual symmetry also there. And we labeled that guy with charge M, and here it is some operator M hat. And yeah, we want to sort of, if we want to study the spectrum of this model, we want to organize it in terms of this an eigenbasis of this residual symmetry. Now we looked also, to do that we used some general formulas, or we wrote down some general formulas for the twisted monotomy matrix after doing such a Drinfeld twist. So in the usual case, we have this nice product of our R matrices over some auxiliary space, and then and the physical space as well. And then after the Drinfeld twisting, this gets this nice structure where we have some overall similarity transformation of your physical spin chain, but then also some Drinfeld twisted additional actions on the usual monotomy matrix, really in the sort of the same analogy as we had here for the sigma model monotomy. Oh, sorry, that should be U. Yeah, I had set everywhere and then I changed it to U. Yeah. So that's a U. And then here we see this very general structure appearing, which in the case of the Jordanian model takes this particular form. And what I want you to focus on is simply that the guy that is first acting on the physical space, which is called this beta A, will be realized through the symmetry operator delta, so the co-product of E on the physical spin chain sides. And then on the other side, we have sort of the opposite version. Okay. Then I totally won't have time to discuss this slide really in detail, but let me just say that we also gave some explicit formulas for the twisted boundary conditions of this Drinfeld twisted spin chain. So in general, the expectation of those guys is that you have this quasi-triangular Hopf algebra that is twisted and defines for you some deformed Hamiltonian with some periodic boundary conditions on the level on the side 0. Sorry, it's side 1 generators. And the expectation is that you can map this structure similar as in the sigma model. You can map it to an undeformed Hopf algebra with an undeformed Hamiltonian and twisted boundary conditions that are realized through some symmetry action. And yeah, I'll just revert to the poster of Adrian for that, but basically we have some gluing procedure where we find the twisted boundary conditions given again by the same object beta that also appeared in the twisted monotomy, which is for the Jordanian case here realized in terms of the residual symmetries. And so for SL2R, we wrote down the specific boundary conditions for the E, H, and F generator that you see here. So then we used those two things, the twisted monotomy and the twisted boundary conditions, to study or to initiate the study of the spectral problem for these models. And we did it in two extreme regimes. So on one side, we looked at the thermodynamic large length limit. And on the other side, we had a small length spin chain with just two sides. And in the thermodynamic limit, we use this connection to Landau-Lifshitz theories. So we start with some undeformed interaction Hamiltonian, which you can take the continuum limit of, as was done by people in the room. And you can look at like the field theory version of this Heisenberg Hamiltonian, and you'll find it to be this type of guy. So for the people that know, it's just like going to some coherent state representation of the spin chain. And we did this same continuum limit at the level of the twisted boundary conditions to see what the fields of this sigma model have to be, and then you'll again find some realization in terms of this M residual symmetry, which is really like the same thing as the co-product of the E operator at the spin chain site. And then we studied minimal energy solutions to this Hamiltonian, and we found that are subjected to these twisted boundary conditions. And then we find an energy that precisely matches the deformed part of the sigma model Virasoro constraint that we had earlier. So here we had this deformation of the BPS operator with this M charge, and here we see exactly the same thing happening. So that's quite nice. We have this from two different perspectives. On one side, it came from the spin chain Drinfeld twisting, and on the other side, it came from studying the solutions of the equations of motion of the sigma model. So yeah, I'll have to wrap up a bit faster now, but we also looked at the small chain guy, and here we used the twisted monotomy matrix. In particular, it was important for us to put the physical spin chain in an eigenbasis of this M hat rather than an eigenbasis of a Fock space states of the Cartan generator of SL2R, where the functional wave function will have this particular form. And then we studied the spectrum of the twisted transfer matrix, which after the Drinfeld twist has these extra combinations here. Let me just mention that you're not really able to do normal algebraic beta ansatz, because there won't be any like non-trivial pseudo vacuum with a non-zero M charge on which you can start the ABA procedure. But what we did was just like, as a first step to looking at the spectrum, is just like do a straight eigenvalue calculation problem of this twisted transfer matrix, rather than using some integrability methods. So that will be, because we're working in this non-compact representation of SL2R, it will become some differential problem that we sort of solved with type of Frobenius methods in some sort of perturbative, in a perturbative way, and the solution has this form. And for us, it was important that here we can show that the spectrum of this transfer matrix really gets deformed if you're looking at a spin chain that is in an eigenstate that has non-zero momentum charge, in the same way as we had also for in the continuum limits, where if m was 0, you would find an undeformed spectrum. But in non-zero m sectors, you do get a deformation. And this is sort of in contrast to what several people have been doing over the years in this case, where if you would organize a spectrum in terms of Fock space states, you would get sort of an undeformed spectrum, because essentially the charge sector will be 0. So yeah, I'm running a little bit over time, but I'll just conclude right now. So I talked to you about Jordanian strings and Jordanian spin chains, where we had on the string theory side this nice classical Lex integrability framework, where we have the two formulations of deformed or twisted, where we had signatures of classical Drinfeld twists. And I didn't mention, but that also allowed us to do some classical spectral curve computations on this particular point-like solution that I mentioned. We had some weird particle production processes in there that we don't really understand, involving massive asymptotic states. Yeah, it would be interesting to also, so here it's clear sort of that we should work in some type of basis of this root generator, an eigenbasis of this root generator, rather than some discrete particle number like a type of basis. So it would be interesting to understand that better and get another notion of this S-matrix integrability in this sense. Then for Drinfeld twisted change, we had some general formulas for the twisted monotomy and the boundary conditions, which in the Jordanian model were in terms of this symmetry operator, and then we looked at the spectral problem, had a match with the string ground state, and also had a non-trivial deformation in the short chain, spin chain. What I didn't mention is that there's some part of the spectrum that we don't really are capturing, so it's not clear how the magnons are realized in the deformation, at least in a continuous way. And for that, we believe that studying this in a non-perturbative framework in the deformation parameter and also at all lengths of the spin chain will probably help. We also did a short initial study of the Q functions, and having a full analytic structure of that will probably also give some insights to the full spectral, well, very likely give insights to the full spectral problem of these cases. And then in particular, it would be quite interesting to take these large J corrections from there and match them with the string theory semi-classical data. So yeah, I hope I sort of convinced you that there's some nice work still to be done for this Drinfeld twisted ADS-CFT correspondence. We're sort of starting to uncover a bit about the spin chain. What is still widely open is what happens at the gauge theory side. And then I think it would be extremely interesting to understand. But with that, yeah, I'll thank you. Sorry for going over time.
Thank you for the nice talk. Are there any questions? Fedor?
Back one slide. I wanted to ask, could you go back one slide? Yeah, so here you introduce these two twists. One is off diagonal, the other one is diagonal. So it looks in many ways similar to what we studied with Kostya and Monica, but also your twist is different because you have this diagonal part. So I wanted to ask, if you look at the non-diagonal part, could you introduce an arbitrary parameter in front of this off-diagonal component? Would it make any sense from a string theory point of view, from Drinfeld twist algebraic construction? Or it has to be equal to 1?
Like yeah, I think I mean, it will also sort of, so it came from the same object, so if I'm changing something here, I'll also change some stuff here. And well, yeah, basically it's just a rescaling of the deformation parameter. But yeah, so there was no like two type of different twists. There's just one twist, this guy here, and it's because of like the opposite action that the R matrix has, that it sort of looks different after it passed through the R matrix. So that's why it's like has this different type of structure.
Kolja?
Just to understand, Natesh, could you explain in basic terms what is the delta of diagonal element which you just looked at?
So
what type of operator is it?
This here?
In this,
just
the on the next to the last slide, which Fedor asked you to show. This
Here?
one. Yeah, what is the delta of H? What type of beast is it?
So this is just a co-product of H. So I'm here in the length 2, so I just like H1 plus H2.
In more basic terms?
Even more basic terms. Well, just a cartan of SL2R on the full length 2 spin chain, the action of that on the spin chain. Yeah, just a physical space, yeah. So yeah, and in particular it's an operator in this case. So here we're not in this, the eigenbasis of delta H, but here we're in different eigenbasis, and so it will be some non-trivial operator.
Okay. Any further questions? Hey, Arkady? Oh, there.
Some of these examples have supersymmetry, right?
Yeah.
TST, but some not?
Yeah.
So which one?
The one that we've been studying has 12 supercharges. Weird number because we're destroying the Poincare subalgebra. But yeah, so this one has 12, but you can also, I mean, really supersymmetry doesn't really play a role here. You could add some additional TSTs. You would have to go to a bigger subsector of PSU 2,2/4, but yeah, I think the same sort of things will go through.
One last question by Claudia.
All these deformations are unitary, and the theory stays unitary.
So I think it depends on how you look at it. There are some non-diagonalizable sectors, probably, which we don't completely understand. But yeah, at this level, I don't really have a problem with the unitary or non-unitary thing.
Would it make sense to study some complex parameters which you introduce, like, for example, those who lead to fishnet theory were useful to some.
Maybe
some interesting limits which would bring some.
Yeah, that could be
integrable models.
Yeah, I don't know, but yeah, maybe yeah. Well, you could connect to the compact representations maybe if you go to the complexified algebra, but yeah, we didn't look at this.
Okay.
Okay, then let's thank Sibylle again. Yeah, 10 and 5 minutes.
Perfect. Is this too loud, too silent, too anything? Oh, you give me a pointer. I just.
Yes.
Perfect.
And the laser is in the center.
Oh yeah, perfect. Great. Is this loud enough? Is this good?
Okay, then we move on to the second part of the second talk of this session by Beatrix Newman, who will talk about a microscopic realization of DS3. Okay, please go ahead.
Well, thanks so much for having me here. So I think this is a little bit different than the talks we've heard so far. So please bear with me and, I don't know, just interrupt me during the talk or anything. Like, I'm happy to answer questions during the talk as well, so we don't lose too many people. So today I'll be telling you a little bit about a series of papers that we wrote in collaboration with very brilliant collaborators, Scott Collier, Lawrence Eberhard, and Victor Rodriguez. I think Lawrence should be in London. He's on his way here. So very good. So zooming out, just so you really have a takeaway message, is we had like lots of beautiful talks about like ADS CFT. So, but we're living in a space-time that's asymptotically distributed. And there's a dearth of controllable models of quantum gravity in expanding spacetimes. And I think it's pretty fair to say is that there's no unifying picture of de Sitter quantum gravity that comes close in scope or rigor to anything like ADS CFT. And I think basically this knowledge that we have this expanding spacetime, that we need to understand this, and combined with the lack of any unifying picture, is what really motivated in the last few years a lot of us to go to low spacetime dimension. By low spacetime dimension, I mean 2 spacetime dimension and 3 spacetime dimension. So we are not neglecting 4-dimensional real world, but we are just like going down in dimension, trying to get as much insight as possible, and then trying to use this insight that we got in low dimensions to learn something about the 4-dimensional world. And in particular, we are hoping to really get a controlled setup in which we can study, for example, a microscopic model for de Sitter quantum gravity. And in this talk, what I'll focus on is 3-dimensional de Sitter, so 3 space-time dimension, 2 space, 2 one time. And I'll tell you a little bit about this concept of canonical quantization, so we will build a Hilbert space. I'll then tell you a little bit about the wave function, and I know many of you will not come from this, so but like bear with me in this wave function discussion, so this is like a little bit different like than maybe this Hodel-Hawking wave function that you've heard so far. I'll then tell you like how we are tying this like this 3D de Sitter world to a string theory, and the string theory is known as we call this string theory the complex Liouville string. I'll then tell you how we are tying this string theory to a matrix integral, and this matrix integral is then going to give us all the observables in this theory. And then like, so I'll go to a Euclidean picture, or like a static patch de Sitter perspective. So static patch de Sitter perspective is really us. So we as an observer are surrounded by a cosmological horizon. Gibbons and Hawking told us that there's an entropy associated to this horizon. And I will tell you how this entropy is talking to any of those string theories and matrix models. Very good. So let's just like jump into it, and please like interrupt me. I know this is a little bit different than what we've heard so far. So the canonical quantization of DS3. Right. So we start with 3D Einstein gravity with positive cosmological constant. So this is this Lorentzian action over here, where notably lambda here is positive. So lambda is related to the de Sitter length as in this following way in 3 dimensions. So this theory with lambda positive is loosely related to SL2C trans-Simon theory. So this is different than lambda negative. And lambda negative, this is SL2R times SL2R. This is lambda positive, so it's SL2C trans-Simon theory. My like saying loosely here is just that there are important caveats when we are trying to relate this metric formalism to the trans-Simons formalism. Notably, like for example, the invertibility of the metric, the global structure like SL2C, PSL2C, and so on and so forth. Large diffeos that are gauged in the gravity theory and not in the trans-Simon theory. So you need to be very careful if you're jumping between metric formalism and trans-Simons formalism. Okay, but so we will now take some slice. So some slice of this 3D de Sitter, which is like a 2-dimensional surface. And I call this 2-dimensional surface, this initial value surface sigma gn. I call this 2-dimensional surface sigma gn. And for the sake of this talk, I will always push this sigma gn to be squared plus, so be the infinite future. And moreover, in this talk, I will always assume that my sigma gn is compact and hyperbolic. So I'll always assume that 2g minus 2 plus n is bigger than 0. So G is the genus, N is the number of punctures. So in particular, I will never let sigma Gn be the sphere, or like the torus without any punctures. Right, so then we will take the phase space of this initial value surface sigma Gn, which consists of the metric and the extrinsic curvature. And then, as in quantum mechanics, we will choose a polarization. And the choice for us is that we will make the wave function depending on the metric only. And moreover, what we need to impose are these 2 conditions, like this etheric gravity. So we need to impose the DeWitt equation, which is nothing else than this Hamiltonian constraint, and the momentum constraints over here. And in particular, these 2 conditions are going to make my wave function to be a function of this quotient space. So from this, with the Witt equation, I get like and the momentum condition, I get this diff times vowel. And now 3D comes as a savior, because in this case, where the initial value surface is two-dimensional, this quotient space is nothing else than the moduli space of this surface sigma gn. Very good. So now, okay, depending on how we are looking at this quantization, we need to take into consideration, as I mentioned before, that if you're going to do Chern-Simons formalism, in Chern-Simons formalism, you're not gauging the large diffeomorphisms, you're only gauging small ones. So to really relate the gravity theory to the Chern-Simons formalism, we need to gauge the mapping class group, which is nothing else in this ratio between large and small diffeos. But then in the end, so my Hilbert space is going to consist of functions, well, sections, but okay, whatever, of functions of this moduli space mgn of this surface. Very good. So far, so good. But then if you really properly go through this derivation, so go impose this momentum and this Hamilton constraint and this wave function psi, or if you just use some DSCFD jargon that you know in the back of your head, you're going to find that like these conditions are really some Virasoro word identities. And from these Virasoro word identities, you can read off that your wave function psi transforms like a CFD correlation function with a central charge and a specific conformal dimension. And the central charge that you can read off from these Virasoro word identities is 13 plus something imaginary. So here, the tilde really means that there in principle could be further imaginary corrections. But the one loop piece, which is the 13, is the unique real part of this central charge. And the conformal dimensions, which are the combination of left times right movers here, they're given, they're in this form 1 plus IR. So in particular, they're in the principal series representation of SR2C. Now this intermediate part over here, this is DSCFD, so which relates the conformal dimension to the mass. And so if you want this square root, so this ingredient of this number inside the square root to be negative, so that this is purely imaginary, you can read off that m is of the order 1 over L de Sitter. So these are heavy particles. Just hold on a second. So in principle, what we're talking about, we have some punctures, and these punctures extend to some Wilson lines of some non-dynamical particle in the bulk. So this is pure 3D gravity, so there's nothing dynamical. There's a punctures that extend in the Wilson lines in the bulk. Yes? How do you get? Oh yeah. So this you basically like read off from this. Like if you look at the Chern-Simons formalism, and then you impose this constraint. So if you really properly go through this imposing this condition, you can just read off the central charge. No. Right. Well, I mean, there could be further corrections. So this is the tilde. So there could be further like G Newton over L corrections, but that are all imaginary. Very good. And okay. So for the sake of this talk, and this will pop up later, it's often convenient to parameterize the central charge using this B parameter here. And if you compare these two different things, so these two things, then in this parameterization, B squared has to be purely imaginary. So this will just be useful later. Very good. So we have a wave function. The other thing that we need is some sort of inner product. And the inner product that we will take is nothing. It's just like, okay, some pretty standard inner product. So we throw in psi and psi prime, which are living both in this Hilbert space HGN. And then we're considering psi star, and we're dotting this with psi prime. So this, you can forget about it for now. If you're interested in this prefactor, which is actually important for us, come ask me later. For now, this is just a normalization. But now, in particular, because we are dotting psi star with psi, the imaginary pieces drop out. And so the central charge of this object in here is like C plus C star, which is 26. Perfect. So this is perfectly well something we can put into this moduli space integral. And the total conformal dimension of this thing over here is T. Okay, and you can also see that it's spanless. So in principle, like this object over here, like the right-hand side of, I think for you, the right-hand side, yes, the right-hand side, like this side over here, is nothing else than a string theory path integral. Very good. So now let's go into so we have the wave function, let's look at what kind of wave function does this state describe. So we consider the following universe. So remember that I told you that my scribe plus, which is my surface sigma gn, is compact and hyperbolic. If I'm imposing that, the scribe plus is compact and hyperbolic, so in particular this thing over here has richest scalar -2. But if I want this whole thing to solve this 3D and Hilbert equation with positive cosmological constant, then what I need to put here is a sinh. So if you know global de Sitter, in global de Sitter this sinh is a cosh, and then it has this like this hyperboloid structure. In this case, because indeed this sigma gn is compact and hyperbolic, I need to put this sinh over here. And in particular, what this means is that this spacetime has a singularity at t equal to 0. So this spacetime has a bulk singularity at the point t is equal to 0. So this is a Milnor type singularity. And this is a very interesting point, but I think for the sake of this talk, I will not have time to explain this in detail, is that this wave function now differs significantly from the Hartle-Hawking now boundary discussion. But for us, it seemed to be the suitable object to consider in three-dimensional de Sitter. Very good. So now, given this boundary condition, so given the fact that we have this boundary condition at square plus and this boundary condition here at t is equal to 0, which in the Chern-Simons formalism means that A is equal to A bar, so you have the gauge field A. And so to have like a vanishing Zweibein here, you need that the gauge field A is equal to A bar. So given these boundary conditions, the unique wave function, at least as far as we know, is given by this Liouville correlator. So I'll explain in a few seconds what exactly Liouville theory is, although I think there are some experts in the room that know what Liouville theory is better than me. So the wave function for this genus G and number n of punctures is given by these correlation functions. So V over here are vertex operators in this Liouville theory that I will explain in a second. And I will label the conformal dimensions by some p's, which are called the momenta. And the p's are related to the conformal dimension this following way. So remember that I said my delta from the canonical quantization was of the form 1 plus IR, so it was in the principal series. The central charge was 13 plus something imaginary. So that in particular implies that the pi squared is purely imaginary. Very good. And this wave function now has a bunch of very desirable properties. So this wave function, just given that it's Liouville theory, it factorizes under the generations of square plus. It is crossing symmetric in and on itself, so I don't need to like sum over any topologies. I don't need to do any fancy things for this wave function. This is crossing symmetric in and on itself. And it is a normalizable wave function. And to that we will also get in a second. Very good. So very good. And now what we can form are observables. So what are the observables in the game? The observables in the game are cosmological correlators. So this thing here is what Malasena in 2002 called cosmological correlators. For the sake of this talk, this paper, we called them integrated cosmological correlators just because there's a lot of confusion in literature that didn't integrate the cosmological correlators. But if you really want to have gauge invariant observables, you better integrate them. And so these are just the gauge invariant observables in this game. And so you take a bunch of like operators, and then you put them into this integral where you integrate over all the metrics on square plus with your wave function. Now taking the wave function to be the Liouville correlator, this object over here is nothing else, just like carefully written out. So we have the metric when we just carefully divide by diff times val. This is just like, I didn't put this here just like for the sake of convenience. But in principle, we would have to like really divide by diff times val, and then we put in the wave function. Now, the reason why I don't put any extra O's is because these are really massive particles that backreact and modify my wave function. So I'm just doing the de Sitter quantum gravity, not the de Sitter QFT on a de Sitter background. This is not rigid de Sitter. This is the de Sitter quantum gravity. Very good. And if some people are very happy with me summing over all genera, some people are not. I'll give you a motivation afterwards for why this is very obvious in our game. Or let me give it to you already now, kind of. So the reason why we're summing over all genera over here is because we're going to relate this expression now here, which are these cosmological correlators, to some string amplitudes in some string theory. And the string theory we're going to relate to a matrix integral. And in the matrix integral, we are not asked, we have to sum over all genera. So the matrix integral backwards tells us we need to sum over all the genera here. So now what I'm going to do now, and how much time do I have left? Perfect. So in the next 15 minutes, I'm going to tell you how we're taking this cosmological correlators over here that we got from a canonical quantization of 3D de Sitter gravity. How we are relating this object over here to string amplitudes AGN of a two-dimensional string theory, and how this two-dimensional string theory is nothing else than a matrix integral. So are there questions here? This is a lot of things. Oh, this is just because I'm integrating all the matrix here. That's what I mean, yes. Very good. Good. So let's look at these AGNs. So far, this is a bit mysterious object. Now let me give you the AGNs for arbitrary G and N. So, and I'm going to give you the AGNs through this string theory that's called the complex Lorentz string. So the complex Lorentz string is the following 2D string theory. It takes a Lorentz CFT. So Lorentz CFT is a two-dimensional CFT. It's a non-compact CFT. That means it has a continuous spectrum and a non-normalizable vacuum. And so I'm taking this Lorentz CFT to have central charge 13 plus I times lambda, lambda being any real number. And I'm pairing it with its cousin, which is its complex conjugate. So in such a way that the total central charge of these two things adds up to 26. And so it's killed by the BC ghost. This is just a 2D string theory now. And now, as a 2D string theory, what I need to impose is the mass shell condition. So I need to impose that the conformal dimension of this theory, of the vertex operator of this theory, the conformal dimension of the vertex operator of this string theory add up to 1. And that in particular implies, in terms of the momenta of these vertex operators, that they are tied in the following way. And this is a string theory. If you look at H plus H tilde, so the left and the right movers, it's going to tell you that the conformal dimension is 1 plus IR. But let me just stress out here. So let me just make this point clear. Here, now I'm taking a string theory. So I'm just imposing the mass shell condition on a string theory. And imposing the mass shell condition on this string theory gives me delta is equal to 1 plus IR. This is nice, but previously the delta is equal to 1 plus IR I got from a canonical quantization. So they happen to be the same, but the way that we got them are different. So, and the observables in the string theory are the string amplitudes. String amplitudes are the following object. So you take the correlation function of this theory, take the correlation function of this theory, and you put in the BC ghosts. And the fact that there's an absolute value squared is because I have Lorentz CFT with Lorentz CFT star. So that gives me this absolute value squared here. But now this is nothing else than what we found previously as a unique solution of the wave function. So this AGN is nothing else than the integrated cosmological correlator of 3D de Sitter quantum gravity. And so I have my AGNs now for arbitrary. I have my AGNs defined as string amplitudes of some two-dimensional string theory. Now this is wonderful. And computationally, I can look at the string amplitudes for some low G and N. So for like the 4-punctured sphere, for the 1-punctured torus, I can put this on the computer and calculate this. This is really because these integrals are absolutely convergent integrals. This is because this is lower CFT, and in this lower CFT, these things are absolutely convergent. But it's still hard. To really push this to arbitrary G and N is really, really hard. However, the savior is a matrix integral. So, and let me just point this out. So what I mean by a matrix integral here is a double-scaled matrix integral. So this is notably different than like the 80s, 90s discussion of a matrix integral. So double-scaled for me is a limit in which I already took the size of the matrix to infinity and zoomed into a specific region of its eigenvalue distribution. So I give you this finite n matrix integral over here, but just to tell you that this is where it originally came from. But I don't have access to this finite n matrix integral. I just know that something of this sort was the starting point. So, but the starting point indeed was like not a single matrix integral, but a 2-matrix integral. And a 2-matrix integral with 2 Hermitian matrices, M1 and M2. So then I take this Hermitian matrices, M1 and M2, and I have a potential for M1 and a potential for M2, and I have this interaction. And observables in the matrix integral are resolvents. Resolvents are given by this trace. So I could look at resolvents for one matrix. I could look at the resolvent of the other matrix. If there's no superscript, it means the resolvent of one matrix, but this is an arbitrary choice. So, and then in this double scaling limit, so in this limit in which I take my size of the matrix to infinity and I zoom into a specific region of the eigenvalue distribution, these products of these resolvents have this genus expansion over here. And what I'm after now is I'm after trying to find these coefficients RGNs. So the RGNs follow from a sort of loop equation, which is now, or which I will introduce as a topological recursion. So let's take this a little bit of a step back again. So let's look at this resolvent again. So what you can see here immediately, so in principle there's an identity here. So whenever x hits one of the eigenvalues of M, this thing is going to have a pole. If I take the size of this matrix to infinity, these poles are going to smear out and going to form a branch cut. So my resolvent in principle is a multi-valued function that's going to have branch cuts whenever it's going to hit some of the eigenvalues of this matrix. So because I don't like multi-valued functions, what I'm going to introduce is a Riemann surface on which my resolvent is going to be single-valued. And this Riemann surface on which the resolvent is single-valued, that's called the spectral curve. So, and for the specific, for the complex Lorentz string, we found that the correct spectral curve is given by, is parameterized by these two functions, x of z and y of z. So it's these two trigonometric functions. And just if this was a bit too abstract for you, one thing that we can get from the spectral curve is the eigenvalue distribution. This is because the spectral curve is really related to the resolvent, and from the discontinuity of the resolvent, I guess many of you might know is that from there we can get the eigenvalue distribution. So looking at the discontinuity of the resolvent, we can get the eigenvalue distribution. So for example, this is the eigenvalue distribution of one of the matrices. If you look at the discontinuity of y of z, you will get the eigenvalue distribution of the second matrix, which is just a mirror symmetric expression over here. So, and it takes the following form. So the 2 is just a normalization. So we start at 2, it goes up, and then it goes down. And then something really, really bad happens over here because the eigenvalue distribution should not be negative. But I will get back to this later. Very good. So, and now we are done, because now we plug this into what's called topological recursion. So we plug the spectral curve into the topological recursion, which takes starting point omega 0,1 and omega 0,2. So genus 0, one puncture, and this is defined in this following way. Omega 0,2 we can borrow from this result of Einard and Orantine because it's always the same for every Hermitian matrix integral. And then the topological recursion is a recursion in G and N and gives us recursively the omega GNs. So these things over here. And the omega GNs are related to the RGNs, which are these coefficients of the product of the resolvents. So if we have all the RGNs, we have solved the matrix integral. And now, okay, finally, there's a relation between the omega GNs and the AGNs. And so once we have all the omega GNs, we have all the AGNs. So we can basically find the string amplitudes, which are nothing else than the cosmological correlators from a topological recursion recursively. So, and what was really hard before now becomes a recursive problem. So, and in particular, you can even develop some kind of Feynman rules to really get this cosmological correlates for arbitrary G and N. So here, just for simplicity, I wrote down A04, but you can go to like A105 if you so want to. So I think in the paper, even we report about like A52 or something like that. So it's pretty straightforward. So it takes this form, but I think for the sake of time, I will not explain you the details, but please just like come and ask me. So actually, how much time do I have? Perfect, yes, perfect, that's perfect. So, but okay, so are there questions? Because now we're gonna switch gears a little bit from a very like global perspective, so like integrated cosmological correlators, to a more like static patch de Sitter perspective. Yes? Oh, it's you need to take the residue, evaluate it at some branch points. We have it in the paper. So I mean, it's, yeah. Do you know the work of Sarchenko Stanford? It doesn't, okay. It's a known relation. It's a known relation. So, okay. So now let's switch gears then, and let's go from like this square plus, which was in this like global de Sitter Penrose diagram over here, to us. We are having our little world line over here, and then we have the event horizon that's surrounding us because of the expansion of spacetime. And now, notably, if you rotate static global patch de Sitter Euclidean signature, you're getting the sphere. So this is the sphere over here. Very good. In Gibbons and Hawking, much inspired by the results of black holes, conjectured that the cosmological horizon encodes an entropy. And this entropy is, according to Gibbons and Hawking, given by the sphere partition function. So in the case of 3D de Sitter, it's given by the 3-sphere partition function. 4D de Sitter is given by the 4-sphere partition function. So basically, you kind of like the Wick rotation of the static patched Euclidean signature. So you take this gravitational path integral, which is a Euclidean gravitational path integral on a 3-sphere here, and then you hit it with the logarithm. So this is just, in principle, this is like Euclidean thermodynamics. It's just that in the Sitter space, the energy is 0 because the Cauchy slices are compact. But in principle, if you add some E over T over here, then this is just Euclidean thermodynamics. So this gravitational path integral over here was obtained to one loop order in this paper over here from the Euclidean Einstein-Hill production. And what you find is that hitting it with the logarithm, you get these contributions. So this first part over here, pi L de Sitter over 2G, is nothing else than the area of this horizon. So you have this horizon over here. So this horizon. So the area of this horizon you calculate to be is given by 2 pi L de Sitter. Then you divide by 4G newtons. So this is like the standard, like in principle, black hole area of 4G, which is in this case true as well. So, and this leading piece is the fact that this gravitational path integral on a sphere really evaluated to leading order to area of 4G. That's really what like pushed the Gibbons and Hawking conjecture. Then the next contribution that you get from this gravitational path integral over here is like a log with a coefficient that in ES3 is 3. So it's related to the dimension of the symmetry group, so SO4, sorry, the dimension of the symmetry group of the sphere. So for the 3-sphere, it's SO4. For the 4-sphere, it's SO5. So it changes depending on which dimension you're living in. In 3D de Sitter, it's 3. And then you get another log correction. And then you get this kind of infamous phase over here, which is the Gibbons-Hawking-Paré-Polchinski phase, which you get because the Euclidean gravitational path integral is Gaussian unsuppressed. So there's this conformal mode problem, that Euclidean gravity, in principle, the conformal mode is Gaussian unsuppressed. And how Polchinski and Gibbons-Hawking-Paré solved this is by Wick rotating the field. And then you end up with another problem, and I'm happy to explain this in more detail, but this other problem is that you rotated a few modes too much, and a few modes too much, then you needed to Wick rotate back. The number of modes that you Wick rotated too much in 3D de Sitter, sorry, for the 3D path integral is 5. So that's this 5 over here. The 5 doesn't matter. In principle, this is an I. So 5 pi I over 2 is pi I over 2, like, I mean, so it's I. And OK, then you can get further corrections over here. OK, so this is a gravity slide. But why am I telling you about this gravity slide? Before I told you about the matrix integral. Now let's go find these numbers from a matrix integral. So, OK, so I had this matrix integral. I had a matrix integral, though, which was not a finite n matrix integral, but I had a double-scaled matrix integral. So I took the size of this matrix n to infinity. So a priori, like if I would tell you like how many degrees of freedom like are left in this matrix integral, you would tell me, oh, it's infinity because I took n to infinity. But now let's look again at like the eigenvalue distribution that I had before. So, and this eigenvalue distribution had this following form. So it started somewhere, it went up, and then it went down, and then it had a bad regime in which it went negative. This is bad. Eigenvalue distribution should not be negative. Let's close our eyes, and I tell you now, like we have no a priori reason why this is okay. This is just seemed to work. It would really need a better explanation. So let's just stop here. Let's just assume all there is in this matrix integral is this blue shaded region. If you're really careful, like you can actually find that at this point here, non-perturbative effects start playing a role. So far, everything was perturbative. At this stage, actually, when the eigenvalue distribution hits this 0, that's the location in which non-perturbative effects have to start taking into consideration. So at this stage, something has to happen, which would render this eigenvalue distribution non-negative, but we don't know what exactly. But let's just close our eyes for now and just assume that everything that's left in this matrix is this blue shaded region. And let's take the eigenvalue distribution and integrate it from 2 to this point x naught. So the eigenvalue distribution we had, then we can perform this integral exactly. So this tilde over here just means that I forgot some pi's, but we can do this integral explicitly. And then what we find is this expression over here. There's also this genus counting parameter that we had to fix using some DQFT machinery. But okay, fix this e to the power of s naught parameter. Great. Now take this expression for the effective number of degrees of freedom. Now remember that there was a relation between this b parameter and, in principle, L over g Newton. So, which came from like parameterizing the Liouville central charge in this following way, and then taking the central charge as we got it from the canonical quantization. So that tells you that b is of order is something like IL over g Newton or something like that. Plug this into this value of b in here and do a semi-classical expansion. Furthermore, okay, hit it with a logarithm. The square over here you can understand, for example, with the fact that we have two matrices, so we need to have take an effective squared. And then if you do a semi-classical expansion of this expression that we get from the matrix integral, the numbers that it spells out is like pi L is over 2g, which is area over 4g. 3 times logarithm of area over 4g, plus 5 log 2 pi, plus pi I over 2. So the numbers that the matrix integral knows about are the same numbers that the gravitational path integral gave us. So basically this matrix model entropy agrees with the Gibbons-Hawking proposal, which came from a gravitational path integral. Go ahead. You can, in principle, so it's, this tilde here is significant, because this tilde could have been slightly different, and then it would have given it the opposite sign. So yes. In principle, we have an ambiguity, yes. Right. So that's it. That gets me to my. That's an interesting question. It really comes from here. So, I mean, of course, this thing, viewed simply from a matrix integral perspective, it should be real. It's just counting an effective number of degrees of freedom. It really comes from this consistency of the DQFT that fixed e to the power of s naught to be b inverse. So it really comes from here. And to be really honest here, so this tilde is really significant. So we could only fix this up to some constant numbers. So maybe in the end, we were too quick. The interesting thing was that, I don't know, still, it gave a face if you were, ignoring these constant factors. Very good. So as a summary, and I think I'm really out of time, kind of, yeah. So we had this relation between integrated cosmological correlators and the double-scaled matrix integral. This wave function was then, the wave function we looked at was some expanding spacetime. And we saw that log n effective squared, which is the number of effective degrees of freedom in the matrix integral, reproduced the Gibbons-Hawking de Sitter entropy. And I'm really out of time, or am I kind of out of time?
A few seconds.
Okay, so there are some open questions. For example, so far the Hilbert space that we looked at is an infinite dimensional Hilbert space. So it would be very interesting to know, is there some normalizable basis? Is this Hilbert space finite dimensional, infinite dimensional? What is it? I only looked at the sphere. There's lens spaces. What are lens spaces? What is the role of lens spaces in the matrix integral? What happens if you add an observer? Can we put more supersymmetry? Is the supersymmetry, for example, lifting this eigenvalue distribution already? Is that the savior? So is supersymmetry the savior here for us after all? There's a bunch of more questions, but I'll leave it at this. Thank you so much.
Thank you for your talk. We have time for a few questions. Kolya first.
So the fact that density become negative, that means there is no consistent large n limit of this matrix model, or the true saddle point has multiple cuts, or what's going on here?
There's not a unique completion, because you could deform the eigenvalue distribution in whatever way you want.
But matrix integral, is it defined as an integral?
Yes.
So there should be a large n limit of it.
Yes, there should be some way, yes. Yes,
there should be a saddle point which counts it. If it should be saddle point of the root distribution which corresponds to true large n limit of the matrix integral if it's well defined, and it cannot be negative, right? And
No, exactly. So like the fact that it becomes negative has to be cured somehow, yeah.
so it should be multi-cut distribution of the true saddle point then, or something like that. Like two-cut. Like not to single support.
No, yes. There's definitely more, yeah, multi-cut, yeah.
At a certain point, you wrote down the spectral curve for starting your recursion relation. Is this spectral curve somehow related to some kind of two-dimensional dilaton gravity, like in JT, or something that you derive from nowhere?
We derived this spectral curve from scratch, imposing so basically we started with the string theory, we calculated AGN for like some low G and N, also using some technique that's called higher equations of motion, and basically because lower theory is solved, we knew exactly what poles, what zeros, what everything like had to be, and so that's how we got our x of z, y of z. There is a spectral curve of JT gravity, which is like x of z is equal to z squared, and then y of z is some sign. And basically, the reason that we can never transform this into like z squared is the reason why this is a two-matrix integral. So the one thing that I can say, for example, is that if there are experts in the room, that they might have seen this spectral curve before, because if B is of the form square root of P over Q, this is the spectral curve of an arbitrary PQ minimal string, which is very interesting. But of course, because in the PQ minimal string, the B is like the form P over square root of P over Q, the properties of the spectral curve are very different. So, but yeah, so like this is, yeah, I think this is all I have to say.
Yes, understand.
But we kind of experimentally backwards engineered a spectral curve that satisfied the properties.
About halfway through your talk, you had this sum over genus. So you had this factor G string here.
Yeah.
What do you mean by G string in this model?
I mean, G string is related to it's some genus counting parameter.
So okay, so it's not e to some phi.
No, well, it's related to G string inverse squared is related to like this e to the power of 2 s naught, and so s naught is the leading piece in the gravitational path integral. So NC S2B is some constant that we fixed using this 3-point function. I think I confused you more than I helped you, right?
That's okay. Okay, thanks.
You can fix G string in principle using some TQFT machinery.
All right.
One final question.
Hi. Very interesting, of course, this observation, and I have many questions because I know so well this.
There's a long break. Happy to help.
Never noticed something like that. My question is, at some particular G, in principle, you obtain usually the C equals 1 matrix model, matrix quantum mechanics, etc. Do you have this value here?
That would be incredibly interesting. It's still a really interesting question that we don't understand how the C equal to 1 matrix integral in matrix quantum mechanics pops up. We don't know. This is always a matrix integral.
Because there you have access to effective action, does Javidsky action, so you might have then the real de Sitter picture.
Yeah. It would even be incredibly interesting, like all of this matrix integral machinery, like all of these matrix integrals, they really lose topological recursion. It would, for example, also be incredibly interesting to see if there's a topological recursion for the C equal to 1 matrix integral. For the C equal to 1 matrix quantum mechanics. So, but we just don't know, like why is C equal to 1 so different? So why is that suddenly a matrix quantum mechanics and not the matrix integral anymore? So I don't know.
And another natural question, do you have here some way to the double scaling limit, sum over genera, etc., like we usually do in...
Yeah, I mean, in principle, like our matrix integral from the get-go is double scaled. I always consider...
Double scaled, what essentially you get classical algebraic curve, but I mean, there is a standard way for minimal models, etc., which leads to Pendever-1 equation, etc., the summing up over all the genera. Do you have something like that here?
No. Like I don't think I have like some Pan-Levet type equation. I mean, maybe I could get it, but I don't know.
Thank you.
Okay, then let's thank Beatrix again. And we meet again after the coffee break. you know, 10 minutes, 5 minutes.
I was thinking of that. That's getting it out. No, they should. Red light.
Oh, yeah.
I was afraid.
And it was that beeping at 5 minutes.
Yeah. Rotating lights.
Yeah.
Sirens.
Unfortunately, I did that when Okay, hi everyone. Welcome to the last talk of today. We have Nicholas Bijzet, who will tell us about Magnon kinematics from algebraic reduction. Thank you. Go ahead.
Okay, yeah. Switch that on. Can you hear me? Yeah? Okay, good. Yeah, thanks a lot for the invitation. It's a pleasure to speak here at IGST in London. After 10 years, once again. So today I'll talk a bit about classical and quantum algebra related to magnons, some old stuff. And this is work to some extent already done with Diego Im, and also work in progress also together with Hannes Malcher. So just as a overall scope, so we do have an exact S matrix for Magnon scattering on the worldsheet, and the way it was first found was through symmetries. So in fact, this S matrix can be fully constructed through or as usual in integrable systems, you can construct an S matrix fully through the extended quantum symmetries or classical quantum symmetries. And of course, we know that this S matrix or R matrix has found multiple applications in ADS-CFT integrable systems, but it's also a somewhat particular S or R matrix for quantum integrability, for quantum algebra, in the sense that it, for example, doesn't have a difference form, and thus there are also a couple of open questions, in particular regarding the symmetry. So for example, what is the complete symmetry algebra that is related to this R matrix? Are there any extra symmetries? How about boosts that allow you to go from one reference frame to another? Or maybe there are some central charges. Also, what could be the relation to standard quantum algebras? Standard, I mean simple quantum algebras, for which quite a lot is known. And finally, can we construct a universal R matrix for that resulting algebra then? And then if you want to obtain a universal R matrix, it's probably useful to know the full complete symmetry algebra. So for the purposes of this talk, my goal will be the formulation of a complete symmetry algebra for this Magnon scattering picture. And I'll just start with a bit of motivation. Or the status quo. Then I will present how you can obtain this algebra from a more standard Poincare type affine symmetry or super algebra. And at the end of the talk, I should comment a bit more on the quantum aspect, but start first with the classical one. So here, as a reminder, of what we know about Magnon scattering, or for this R matrix, it basically all started with, say, a dynamic spin chain obtained from n equals 4 super Young-Mills, and I will mostly refer to the most symmetric system, which is n equals 4 super Young-Mills, but to some extent, of course, also this R matrix has applications in slightly lower symmetries and lower symmetric systems. Anyway. So here, the usual QQ relation has an energy coming out, and the unusual feature for this dynamic spin chain was that you can also find non-trivial Lie brackets or supersymmetric Lie brackets for these supercharges of the same type. And that led us to this PSU 2/2 super algebra for the Magnon picture with an additional three-dimensional center. And this three-dimensional center is not just anything, but it had has some curious expressions which relates all these three central charges in a certain way. This is something more like an energy, whereas these two serve more like a momentum purpose for these magnons that travel on the spin chain or on the world sheet. And some improved understanding came about by looking at the classical limit. Classical limit where we take h bar to be small. H bar is 1 over g, or 1 over square root of the 't Hooft coupling. And at the same time, also these momenta should probably be small. And by investigating this classical limit, we found that the symmetry algebra is actually something much like a U2/2 algebra, which is PSU 2/2, but with one additional central charge and one additional derivation. And well, that's somehow different from that picture. We only have one generator P, and we also found an extra symmetry through looking at those classical algebras. It's also a loop algebra, so we do have a spectral parameter that means that all of these generators get lifted to arbitrary loop level in this loop algebra sense. So that is what you usually have in integrable systems. But also, this symmetry admits an affine extension where you have one additional U1 and one additional central charge, something like a derivation that basically measures the level here. And the central charge is something that is sometimes used in affine representation theory of affine Kac-Moody algebra heavily depends also on this central charge. But so far hasn't really found an application in the integrable systems because it was always just 0 for the type of representation we looked at. But that leaves quite a few open questions related to the algebraic treatment. For instance, first, why do we have this three-dimensional momentum vector in the first place? Why do we have these curious functions? Why do they have that particular form here? How does this three-dimensional momentum reduce to merely one generator? And if it does reduce to one generator, why don't we, we should see a two-dimensional picture from the world sheet, which has energy and momentum. So how do these numbers mix up? What is the nature of this extra symmetry L that came about in the classical discussion? And what about their loop levels? Can we make sense of the affine derivation? Is there some purpose of changing the reference frame somehow from one to the other? Or could this derivation even be extended to a Möbius or a Witt or Virasoro algebra? Would that make sense? And then would the central charge of the affine algebra perhaps play a role? And eventually, how can we quantize the full classical affine algebra? So at first, I'll start with the classical algebra here. And just start with this aspect that we have three central charges and try to make sense of that. Namely, this three-dimensional momentum might well belong to a three-dimensional or 2 + 1 dimensional Poincare algebra, which is SL2 cross C3. And it might be useful to relate this to a simple algebra, and the useful relation is to the algebra of SO4 or SO2,2, which is 2 copies of SL2, because you can obtain a Poincare algebra from a curved rotational algebra by a contraction. Contraction means that you just change the generators in a certain way, and then you take a certain limit on this transformation that makes this singular. And in this way, you can obtain from this simple or semi-simple algebra, SL2 cross SL2, you can obtain this non-simple algebra, which is the Poincare algebra. And in fact, this picture has a supersymmetry extension where you basically just squeeze this PSU2/2 algebra in between the two factors. And one can even obtain this as a contraction, as we found out a couple of years ago. And that sort of makes it very exciting for our purposes. So in particular, we do get this exceptional superalgebra D21 epsilon, I called it, because epsilon is supposedly small in this limit. You pair that with an SL2 and you can get a Poincaré extension, supersymmetry extension. Now, why is that useful? Well, we might, if we follow this picture through, we might obtain the integrability structures from a simple classical or quantum algebra or superalgebra, namely this one. And for simple algebras, the construction principles are quite well established, so we could eventually even obtain the universal R matrix from this. It's also curious, the participating R matrices that you get from here. There are two, actually, one R matrix from here and one of there. And once you do the contraction, you sort of marry them up and you cannot take them apart afterwards. So that adds some interest into this picture. And what's also curious is that if you take a loop algebra or an affine algebra of a semi-simple algebra that is a product of two simple algebras, you actually have two independent spectral parameters to start with, and then these even survive in the contraction process. So if you take this honestly, then actually there is an additional spectral parameter which might somehow play a role. And there's also a center which could have some meaning. Okay, so back to our problem. We do have three momenta. We also have three rotations in this Poincaré algebra, and we just want one momentum, but we maybe also want one rotation generator L. And how do we do with that? Well, in 3D, you can just pick a direction. You restrict to rotations around this one direction, and you also restrict to translations along this direction, and that forms a proper subalgebra of Poincaré. In fact, the reduction is a bit different here. For the rotations, you take a subalgebra. For the translations, you rather take a projection. You only want translations in a certain direction. But yeah, that would be a way to reduce this 3 plus 3 dimensional algebra to a 1 plus 1 dimensional algebra that we want. But it's just too plain for ADS-CFT, because once you pick a direction, that might just be a time-night direction, so you just pick a static reference frame and rotations, so that makes it a bit boring, and the ADS-CFT R matrix is not of this form. But instead, you can choose this reference vector here to depend on the spectral parameter in a certain way. If you choose this, say, then this direction of rotation would take this form, and the momentum vector would also take a particular form. And they depend on the spectral parameter in the sense that U times L to the 0 would just mean the first loop level of the L0 generator, and that really adds some new features into this algebra. But still, this procedure works. You can reduce the algebra in this way, and even the co-algebra reduces nicely, but you cannot do this for any arbitrary vector. It has to be basically of a very simple form like this one. And it only works if you do a twist of the Poincaré R matrix in the first place. And the twist is of this form, where you take one Cartan generator and a raising generator. And I'll talk a bit more about that later. There's also the affine derivation that you can get from this Poincaré algebra, or loop affine Poincaré algebra. But in order for this to make sense, you have to adjust the derivation in a bit, because the derivation is just shifting the spectral parameter U here. But if we do shift the spectral parameter U, of course, the form of this L would also change, and it would run out of the algebra. And in order to make it a closed subalgebra, you have to make sure that this one closes with the derivation. And this is done by adding in some extra rotations. However, these have to depend on U, and that leads you to some funny conclusions. Might not be so apparent to you, but
One thing that's very curious is that now you get additional singularities at a certain value of the spectral parameter u, which is plus or minus 2. This is actually where particles, magnons, become very fast, light-like, and once they become light-like, of course, you might expect something strange to happen. But the algebra relations become odd because you have additional poles in here, and that adds some complications if you want to work with it. Okay, let's just try to make sense of what I said so far and wrap up a bit. So if we have a Poincaré algebra, well, the irreps are usually labeled by a mass and a spin, even in 3D. But the states of a loop or affine algebra are also labeled by the spectral parameter u. So the momentum is going to be a function of u, and the energy is also a function of u, and there's a certain relation that was obtained through this reduction. But nicely, it's not just a static picture, because we do have representations with different energy and momentum. We do have extra symmetries. These L's are rotations around the particle axis of motion, if you wish. So that's just a spin generator. And we have ADS-CFT, we have bosons and fermions. They have different spin. So this L will basically rotate the bosons against the fermions. And that's how this works. You can also do this at different u of n. So basically, this adds, for your phase degree of freedom, this adds a momentum dependence. So basically, you can gauge transform your bosons against the fermions. So it sounds a bit like a gauge symmetry, what you have there. The derivation basically shifts u, but since u is coupled to the momentum and energy, it somehow shifts the reference frame. So this d derivation is something like a Lorentz boost, but it's not really a Lorentz boost. You could introduce this special relativity, rapidity variable, and a Lorentz boost would just be a shift of rapidity. But here there's an additional factor of p squared. What's interesting, though, is that you do have here a non-trivial co-bracket for D, and that sort of is what's at the heart of the non-difference form of the S matrix or R matrix, because that D is like a shift of U. If you shift both U's by the same amount and nothing changes, then it's of a difference form. But here you change the U's, and the co-bracket will be non-trivial, and that just means the S matrix changes under such a transformation. So that is non-difference form. But there, you can see this Lorentz boost, but you just have to multiply this d by 1 over p squared to make it a Lorentz boost. So it sort of feels a bit related, but it's not exactly the same. Okay. So that's basically all you can and we got from the classical picture. And now let's take a step back and maybe do something else. So you might know me as someone who sometimes steps out of the ordinary and tells you about things that you don't want to hear about or don't really want to hear about. So I have to be true to myself and do that. And here comes my little commercial break. Namely concerning something about LaTeX. So maybe you want to compose well-balanced LaTeX documents or prepare appealing slides. Maybe not like mine, but maybe you want to do this directly in LaTeX. And of course, as you know, many things work nicely in LaTeX. So, or you take some packages like Beamer, be happy with that. And most of the time that works out nicely. But sometimes you want to do some adjustments or fine-tuning that doesn't really work so well. It's really a hassle to code, and some examples of that might be you want to position included graphics, or you want to compose limiters and change them to your needs, or you want to compose some multi-line equations and they don't come out right the way you want. So maybe you want to handle these aspects more at ease. Maybe you're a person who enjoys both a perfect output and clean sources. If not, then, well, okay, you have to bear with me for a couple of minutes, but I'm certainly such a person, and that's why I got annoyed by things and changed some things. And so out came some packages that you may or may not use. One of them is GraphBox, which allows you to quite easily shift graphics around, or just punch them on your document without occupying space. There is something to code graphics, not using ticks as many people do, but MetaPost is sort of similar, and that's what I use to draw most of my figures. I've also composed some fixes for math mode that I like. But maybe most importantly, I've spent some time this year to write up something on multi-line equations, which allows you to do some options with them. And so I wanted to just use this opportunity or non-opportunity to highlight two packages, namely delimset and this equation lines. And the purpose, motivation is that if you don't know about it, then how could you use it? So I'll let you know about it. And okay, here comes the first package, and just a brief instance of unwanted user support. So this is a package that declares this delimiter structures, which are brackets. Now, if you want to code something like a plus b in brackets, you could just use this command to put the brackets. And you would certainly not do that because it's probably too complicated, rather than just putting the brackets. But yeah, maybe if you want to do more complicated things like commutators or Lie brackets, you could code them in this way, or cats or whatever. You can even custom define some things on the fly. You could do some, if you wanted to do some delimiters like that, you could code them like delim, and then you say opening bracket is this, closing bracket is that, and then you apply it to whatever you like. Or maybe graded commutator, opening and closing, opening square bracket, closing braces, and in the middle you put some character that doesn't really sound like a delimiter, but you can do it. But the nice thing really comes here is that you can change the way they look by simple modifications. So if you were to write this here as a bracket, you could just add a S or C or A in brackets to say this is a square bracket or a curly or an angle bracket. And you can say, well, let's have them a bit bigger or even much more bigger, or even as big as it needs to be. And thus you can easily create some compositions like that. You can even, and that might be useful for multi-line stuff, you can split brackets across lines. So you could say, okay, on the first line I open it, on the second line I close it, and if I want to change something, both of them change at the same time. Unfortunately, you cannot measure how big it has to be, but okay. It also helps you a bit in proper spacing. But on to the second package, if I have more time, yeah. So this is equation lines, and this is about convenient and adjustable multi-line equations, much like in the way you probably use AMS math. But it offers you one environment to rule them all. It's just called equations. There's a short form for equations. You can just use much like this construct that you probably use. You could use that for multi-line equations. I'm here to make your life easier, and that's what I'm doing. You can also put them within equations as a box and use the same short form. But maybe most importantly, you can also, and most of the time you won't need that, but you could modify that, the appearance of your equations. I want to highlight two sample applications again. You can, how about placing numbers in equations, or how about changing the alignment? So yeah, you've probably used multi-line equations with numbers. But if you want to turn them on or off, you have to put stars somewhere. And here the feature is you could just put a star to turn them off in one place, or you could turn them on if they are somehow turned off by default. With another simple character, you just add that. And you could, as usual, number all of the equations and then disable individual ones. But you could also put them as sub-equations with a simple just modifier like this. You could number just a single equation. You could do it with the first one, you could do it with the last one, or you could put it in the center. In normal LaTeX, that would require you some bigger constructs. And here in integrability, we like things like that usually occupied 2 pages before, and afterwards you can just do it in a line, and I'm just doing this on the level of LaTeX here. Okay, you can do other adjustments, and also if the number doesn't really fit where you put it, it will just automatically go elsewhere. So you don't bother with this kind of stuff. Another thing is alignment. Normally you often want to split equations. You have very long equations. You want to split that. You put this in an align box like this one here. But you have to say where the alignment mark is. But the problem comes about when you have equations which are somehow occupying 2 lines. So you have to either accept it like that, or you have to add a bit of space, or maybe even some more space here. But you could also just align it in the way with this new environment. You could just align it in the way that this plus comes right after the equation mark with kind of simple tweaks. You just say, okay, you want the equation mark to come before this character and not after it. You could also do something like gather, where there's no alignment at all, or something like multiplying. But the nice thing is it's all in one thing now. And there are further features like, I'm not going to say that, but you could have a look if you're interested, and hopefully you'll enjoy that a bit. And afterwards you can return back to integrability and go back to quantum mechanics and spend most of your day doing just that. So back to quantum algebra. So my next goal is to derive the Magnon scattering from the quantization of the algebra that I've described in the first part of the talk. And roughly you could think of it in this way. So you have a quantum R matrix which is composed from a rotation generator and a translation generator, typically divided by the difference of the spectral parameters. That's how it normally looks like, and even for this Poincare algebra, it really takes much like this form. But yeah, okay. Now for our purposes, we want a scattering picture, so we want to apply this to the scattering of 2 magnons. Magnons have momenta and masses and whatnot. So we just take a representation of this R matrix for particles, and then the R matrix you could view it as an S matrix. Now, if you just stare at what this R matrix does here, well, the first factor here is an L. It's a rotation. It will rotate the momentum of this particle, but it doesn't do this in a straight way. But it actually does it in such a way that it depends on the momentum of the second particle. So if you have 2 particles coming in, one momentum is rotated depending on the other particle's momentum, and vice versa. And then the next complication is that usually the quantum R matrix is an exponential of some differential operator. Now this is a shift operator. This does an infinitesimal shift. If you exponentiate that, that will be a finite shift. So you have 2 momenta coming in through the R matrix of this Poincare algebra, and it will somehow be the momenta will somehow be transformed from P1, P2 to P1 prime and P2 prime, or as the order is interchanged, it's actually P2 prime and P1 prime. Now, this is a bit difficult to actually compute. So we thought, okay, we can just look at the co-product in this Yangian, which takes a fairly standard form, and derive some relations on these momenta. And actually, these give you 6 relations on 6 unknowns, so you can actually determine what is the outgoing momenta from the incoming momenta without actually touching the R matrix. And in this way, you find a certain transformation of the momenta that this R matrix should generate. I should note, though, that this is not a standard 3D scattering process because we do have particles which are still on a line. We still have the 1D line, the spectral parameters. But the particles have a certain spin, and this spin is a 3D Poincare representation. So that somehow governs how these are transformed. But it's not a real 3D scattering process in that sense. Okay, so now let's recall that we had, for this reduction, we have to reduce this 3D Poincaré representation to one dimension, and that required us to do a certain twist of the classical R matrix. This was the classical twist. It's a combination of a P plus generator momentum and the L0, the Cartan generator of the rotation. So it's a rotation around the z-axis, or, well, actually the energy. But it's a particular kind of twist. It's a non-abelian twist, and it's actually a Jordanian twist that we heard in Sibylla's talk. And if you take the quantum version of that, it takes this form with an exponent of a certain log. Now you can apply this twist to the coproduct, and then you get the coproduct for generators. I've just taken some primitive generators. This might be L plus minus or P plus minus. If you just take that, you'll find that coproduct twists to this form. And that is something that was actually observed in the ADS-CFT Magnon scattering context, where, however, this combination was not labeled as 1 minus p squared, but rather as some generator, which I called U, which was called U, or e to the IP. So if you identify 1 minus psi p plus with e to the IP, where p is this Magnon momentum generator, then actually this form of the coproduct is what was actually found for the coproduct in the ADS-CFT R matrix context. This twist parameter has to be 1 over the coupling, and then you do get for P plus exactly the form that I started with. But this picture so far, I've just replaced P plus by something else, by a different name for this generator. And something like P minus would be very different now. Actually, the Jordanian twist is very non-democratic. It's very different for plus positive charge generators and for negative charge generators. In fact, plus will be very simple. You can even do eigenvalues with that. But P0 would be more complicated. P minus would be even more complicated. But we have to reduce the algebra generators even more. We wanted to go from 3 momentum generators to 1 momentum generator, but we can do this by reducing P minus in much the same way as we changed P plus. We can actually relate 1 minus psi P minus to the inverse of this generator. That creates some relation among the generators, and we can also impose some relation between the P0 and P plus, but P plus at a higher level of the loop algebra. And that would implement the other relation, the last relation for the momentum generators, which we learned in the classical picture, but this is how you lift it to the quantum algebra. And also, the Lorentz rotations can be reduced from 3 individual generators to just 1. And here again, the loop level somehow plays a role. Okay, I should probably come to a close, but I wanted to show you at least this picture here where you can somehow see how these momentum and the momentum reduction and momentum scattering through an R matrix works. So recall the magnons in ADS-CFT are labeled by some momentum, say P1 and P2. And in this giant magnon kinematics picture, you could see them as some pieces of a pie, and they are somehow, if you just line up these pieces according to how they chain up along the chain, you get such a picture. Now, these 3-dimensional or the 2-dimensional px py momenta could be seen as the arrows going from one end of this segment to the next end, and if you chain up these segments in this way, you obtain a sequence of momenta. And what this Poincaré scattering process does for you is it basically just interchanges the order of these two segments of pi, right? So before scattering, you have these 2 momenta P1 and P2 prime, and after scattering, you have P2 and P1 prime. And the way they are related is actually just by using this this non-abelian twist. So the purpose of this non-abelian twist is actually to shift this segment of a pi from its sort of rest position, like the first one, by just rotating it as much as needed to align it with the first particle. And also for the second one, for the resulting picture, you move this segment of a pi from the rest position by some amount to just make it match up with the first magnon. And that somehow seems to be the role of this non-abelian twist, which is curious. And maybe also, what's interesting is that here you do have a proper mass shell relation. However, the mass shell relation is not centered at the center of the circle, but rather at the perimeter of the circle. So magnons at this position here have the lowest energy, whereas the energy raises until this maximum here at p equals pi, and then it sort of reduces back to its usual form. That is precisely the magnon dispersion relation that you have. I don't have really time to mention the affine derivation, but you can lift this affine derivation to the quantum picture, but the problem here really is related to the to these extra poles, and it's very difficult to lift a classical expression to a quantum expression unless you can follow the usual recipes. Here we have additional singularities, so that makes it very difficult. It leaves you, in this construction, leaves you with several ambiguities that you have to resolve somehow, because there will be one expression that works well. And for that, you can change even the classical picture. You can actually do a transformation on the U plane to remove this. Namely, you can do this Möbius transformation, which interchanges these two special points where U is plus minus 2 with psi equals 0 and infinity. And then the points 0 and infinity in the U plane get mapped to psi equals plus or minus 1. It's just a coordinate transformation, but it somehow makes all the algebraic relations in the classical algebra simpler. We hope that we can make some progress with that and then come up also with a proper quantum version, in particular for the shift operator, which should be an additional symmetry for the R matrix. In principle, we can construct it, but it would be much nicer to get the full algebra relations for it. So I think I have to stop at this point with just this one conclusion slide. So I've discussed classical algebra for the worldsheet magnon scattering, and we've constructed basically the full classical picture for it. We've related it to combinations of simple affine superalgebras, and this is nice because for simple affine superalgebras, all the construction techniques can be applied in a more or less straightforward fashion. Even in the quantum, for the quantum algebra, it's straightforward, but it's still very complicated combinatorially. And our quantum construction is thus ongoing. We still don't really have a full picture for this quantum affine derivation, but by investigating it further, we can maybe know or learn more about the non-difference form of the R matrix. We would like to know how the quantum R matrix can be contracted and reducted in much the same way as we did it for the classical picture. And I'd always be curious about other applications of this reduction procedure where you take an algebra and somehow, or not just an algebra, but an algebra with a co-algebra that is a bi-algebra or a Hopf algebra. Take a Hopf algebra, you want to somehow make it smaller. You cannot really normally take a subalgebra because a subalgebra will not really work together with the co-algebra structure. But this reduction scheme somehow takes that into account, and would be, of course, curious to see if we can not only apply this to a simple Poincaré algebra, but maybe to more elaborate algebras. That would be curious to see. So thanks very much for your attention, and have a good afternoon.
Thank you. Thanks for the talk. Any further questions? So I have one question regarding where you had the two R matrices, the D and the SL2 one. You said you had two spectral parameters in there.
Yeah.
And even after the contraction, you still had two free ones. So does that satisfy a Yang-Baxter equation where you would say have a vector of spectral parameters, or?
Yeah, what can I say? You basically have, well, okay. One thing is that in addition to the derivation, you also have a second derivation which does translations in the second spectral parameter. The way this Poincaré algebra works and also this contraction procedure works is basically that you have two identical objects and then you sort of say they are identical up to a tiny bit. Now, you identify the two, that makes two, out of two algebras, it makes you one, and that is, so you just get the Lorentz rotations. But there is sort of a generator that measures the distance between the two, and that's the momentum generator. But this is a small one, it's tuned to be very small. So, or maybe sometimes it's the opposite. But anyway, there's always a large quantity and a small quantity, and the second spectral parameter to a large extent just behaves like it was this, an infinitesimal, just the first derivative part of something. So it's sort of always by construction a linear thing. It's simpler than all the rest. It's much like you take d by d u and just multiply it by v.
I see. Okay, thanks.
But yeah, I don't know what the purpose of it is, and I would be curious to see. I haven't really mentioned that, yeah.
Any further questions? If not, then let's thank Nicholas again. And enjoy the rest of your day.
Location. You can put them tomorrow